There is a moment in the geological record of North America that scientists still cannot fully explain, not because the evidence is missing, not because the data is incomplete, but because the scale of what happened is so enormous, so sudden, and so total that every time researchers think they have pinned it down, something new surfaces that shifts the entire picture. A wall of ice, 3 kilometers thick, once sat over the land you know as Canada. Not thin ice, not a seasonal frost. 3 kilometers of compressed, ancient glacial mass stretching from coast to coast, pressing down on the bedrock with a weight so immense that the land itself sank hundreds of meters beneath it and has been slowly bouncing back ever since. You can still measure that rebound today. The land is still rising. And then, in geological terms, that ice sheet was gone. Not slowly, not gradually, not in the long patient retreat you might imagine when you picture glaciers melting over thousands of years. Gone. Fast enough that some researchers have quietly suggested, in careful academic language, that what happened to the Laurentide ice sheet does not quite fit any model they have for how ice sheets are supposed to behave. This is not a fringe theory. This is not ancient astronauts or lost civilizations spinning stories in the dark. This is published science, produced by glaciologists and climatologists and geomorphologists at major research universities, sitting in peer-reviewed journals, generating ongoing debate that has not been resolved. The question of how the Laurentide ice sheet collapsed, how fast it really went, what triggered the most dramatic climate event in the last 15,000 years, and what it did to the people who were already living in North America when it happened, remains genuinely open, and the answers that have emerged so far are stranger than most people know. Because here is the part that tends to get lost. When that ice sheet was collapsing, North America was not empty. Human beings were already here. They had been here for longer than the standard model used to allow. And when 3 kilometers of ice suddenly released its meltwater into the ocean all at once, when the land that had been locked under glacial mass for 20,000 years was abruptly freed, when the climate of an entire hemisphere lurched in a direction it had never lurched before, those people experienced it. They lived through it, or many of them did not. And the story of what happened to the pre-Columbian civilizations of North America, the ones that built mounds and managed landscapes and followed the caribou across the tundra and fished the rivers that formed when the ice finally retreated, that story begins here, in the cold, in the weight of the ice, in the moment it started to move. If you are watching this to fall asleep, that is exactly why I make these videos. Maybe subscribe and let me know, where are you right now and what time is it? The Laurentide ice sheet was not a single thing. That is the first thing most people get wrong when they try to picture it. They imagine a uniform slab, like a frozen lake, scaled up to continental size. What it actually was, at its maximum extent around 21,000 years ago, was a layered, dynamic, flowing mass of compressed ice that had been building for nearly 100,000 years. It had topography. It had internal structures. It had zones of fast flow and zones of near stagnation. It had ice streams, which are rivers of faster-moving ice embedded within slower surrounding ice that could move at rates that would surprise you if you think of glaciers as slow. It had a calving margin at its edges, where it met the sea, producing icebergs into the North Atlantic. And it had a thermal structure, meaning that the ice at its base was in some places frozen hard to the bedrock and in other places warm enough, from the heat of the earth itself, to be liquid, creating a thin film of meltwater that allowed the ice above to slide. At its greatest extent, the Laurentide ice sheet covered roughly 13 million square kilometers. To give you a sense of what that means, the entire contiguous United States covers about 8 million square kilometers. The Laurentide was larger than that. It covered all of Canada, the upper Midwest, New England, and extended into what is now the northern tier of the United States, as far south as approximately where New York City stands today. The Great Lakes basins were carved by this ice. The Finger Lakes of New York State were scoured by it. The moraines, the long ridges of piled glacial debris that you can still see running across New York and New Jersey and into Pennsylvania, those are the places where the southern margin of the ice sheet sat for long enough to build a wall of rock and gravel from the material it was grinding off the bedrock as it moved. The weight of this ice was doing something to the land beneath it that has profound implications for everything that happened afterward. Geologists call it isostatic depression. the bedrock of the Canadian Shield, which is among the oldest exposed rock on the planet, ancient granite and gneiss that formed more than 2.5 billion years ago, was being pressed down by the weight of 3 kilometers of ice above it. Pressed down not by a little, not by a few meters, but in places by as much as 400 meters. The Earth's crust is not rigid in the way a floor is rigid. Over geological timescales, it behaves more like an extremely viscous fluid sitting on the mantle beneath it, and when you put enough weight on it, it flows, very slowly, downward and outward, and the land sinks. And when you remove that weight, it flows back up. This is called isostatic rebound. And in Canada today, you can still measure it. The land around Hudson Bay is rising at rates of up to 12 millimeters per year in some locations. The maximum rebound since the ice left is estimated at around 300 meters in central Canada. 300 meters of land that has risen since the ice disappeared. This is not ancient history in any conventional sense. It is ongoing. The Earth is still responding to an event that happened 12,000 years ago. Now here is where the conventional narrative, the smooth curve of glacial retreat that gets described in textbook diagrams, starts to reveal its complications. The standard model of Laurentide deglaciation goes something like this. The climate began warming after the last glacial maximum around 18 to 20,000 years ago. The ice sheet slowly retreated northward as temperatures rose. Meltwater flowed south into river systems, and eventually the ocean, sea levels rose gradually, and by around 7,000 years ago, the last remnants of the Laurentide had melted away, with perhaps the very last ice disappearing from Labrador around 6,500 years ago. This is the story. It is broadly true, and within that broad truth, there are events that do not fit the smooth curve. Events that are, depending on how you read the evidence, either anomalies within an otherwise gradual process, or evidence that something fundamentally different happened during specific windows of that deglaciation, something far faster and more catastrophic than the textbook version acknowledges. The first of these events has a name that researchers use carefully because it carries implications: meltwater pulse 1A. It happened approximately 14,600 years ago, give or take, to a few centuries, depending on which dataset you are using and which correction method is applied. During meltwater pulse 1A, sea level around the world rose by somewhere between 16 and 25 meters. The range of that estimate reflects genuine scientific uncertainty. Different researchers using different proxy records get different numbers. But even the lower end of that range, 16 meters, represents an extraordinary amount of water entering the ocean in an extraordinarily short period of time. The event appears to have lasted roughly 300 to 500 years, based on the sharpness of the signal in coral records from Barbados and other tropical sites where sea level can be reconstructed, which means that during that window, sea level may have been rising at rates of 4 to 5 centimeters per year or more, every year, for centuries. The present rate of sea level rise, which is causing genuine concern among coastal planners and climate scientists, is less than 4 millimeters per year globally. Meltwater pulse 1A was moving an order of magnitude faster. Something produced an enormous volume of meltwater in a very short time. The question of where that water came from has been actively debated for decades, and the answer is not fully settled. Some researchers have argued that the primary source was Antarctic ice, pointing to evidence that glacial retreat in West Antarctica may have occurred rapidly around this same period. Others, looking at the pattern of sea level change preserved in different locations around the world, and using models of how the gravitational field of the Earth shifts when large ice masses melt, which can be detected in the spatial pattern of sea level rise, have argued that a significant portion of the water came from the Laurentide itself. The gravitational fingerprint analysis, which is a technique developed in the last 2 decades as computing power has made more sophisticated models possible, attempts to work backward from where sea level rose most and least during a given event to identify which ice sheet was the dominant source. The results for meltwater pulse 1A have not produced a clean consensus. There is evidence pointing to multiple sources. There is evidence that the Laurentide contributed substantially, and there is evidence from the stratigraphy of the ice sheet itself, as recorded in moraines and other glacial landforms, that a significant portion of the southern Laurentide margin experienced rapid retreat right around this period. Rapid is a word that requires some translation when glaciologists use it, because the timescale of glacial dynamics is not the same as the timescale of human experience. But when researchers say that the southern margin of the Laurentide retreated rapidly around 14,600 years ago, what some of the evidence suggests is retreat rates of kilometers per year. In some sectors, possibly faster. The ice streams that drained portions of the ice sheet, particularly the ones that flowed into the Gulf of Mexico drainage basin and the ones that flowed into Hudson Strait and the Labrador Sea, may have surged in ways that pulled ice away from the interior faster than it could be replaced by accumulation at the top. And when an ice stream surges, it does not just melt in place, it moves, it stretches, it thins. And thinning ice, losing contact with the bedrock that helps stabilize it, floating in water if it reaches the ocean margin, is ice that is vulnerable to collapse in ways that ice sitting on solid ground is not. This is the concept that runs through the most alarming scenarios in contemporary glaciology when researchers think about the future behavior of the West Antarctic ice sheet and the Greenland ice sheet. Marine ice sheet instability. The idea that once a marine terminating ice sheet begins to retreat past a critical threshold, particularly if the bedrock beneath it slopes downward in the direction of retreat, which creates a situation where the retreating margin is always in contact with deeper and warmer water, the retreat can become self-reinforcing in ways that are very difficult to stop. The deeper the water, the greater the buoyancy force on the ice front, the faster the carving, the more the ice stream accelerates, the more the interior of the ice sheet is pulled toward the margin, and so on. A runaway process. The question of whether the Laurentide ice sheet experienced something like this during its deglaciation is a question that researchers have been wrestling with in various forms for years. And the Hudson Bay sector of the Laurentide is where the argument gets most interesting. Hudson Bay is one of the world's largest inland seas, covering approximately 1.2 million square kilometers. It was not always a sea. During the last glacial maximum, it was filled with ice. The Laurentide ice sheet was so thick over the Hudson Bay region that the center of the ice sheet, the zone where ice was thickest and had been accumulating longest, was roughly over what is now southern Hudson Bay and northern Ontario. This is counterintuitive because Hudson Bay is now a body of water, and you might expect the deepest part of the ice sheet to have been over the highest land. But ice sheets do not work that way. They accumulate snow on top, compress it into ice, and flow outward from the center of accumulation under their own weight. The center of the Laurentide was over Hudson Bay, not despite it being a low-lying area, but partly because the very low elevation of the surrounding Canadian Shield, combined with the accumulation pattern of precipitation during glacial climates, made that region the core of the ice dome. When the ice began to retreat, the sector over Hudson Bay had a particular vulnerability that researchers have identified as critical to understanding the speed of what happened. The bedrock beneath Hudson Bay slopes. And as the ice thinned and the margin retreated northward and eastward, the point at which the ice was in contact with ocean water extended progressively into deeper areas. Hudson Bay is not particularly deep by ocean standards. Its average depth is about 150 meters, but relative to the ice sheet dynamics involved, the marine contact was significant. The scenario that some researchers have reconstructed for the final collapse of the Hudson Bay sector of the Laurentide is not a gentle melting. It is something closer to disintegration. Once the ice thinned enough that it began to float rather than rest on the bottom in significant portions of the bay, buoyancy forces would have begun to fracture it. Icebergs would have carved into the water. The ice would have broken up from below and from the margins simultaneously, and the meltwater, the water from the ice that was breaking up and floating and melting in a relatively shallow, warming inland sea, surrounded by land that was itself warming, that water had to go somewhere. This is where one of the most dramatic events in the entire deglaciation story enters the record. The event that researchers call the 8.2 kiloyear event, meaning the event that happened approximately 8,200 years ago, is recorded in ice cores from Greenland and Antarctica, in sediment records from the North Atlantic floor, in pollen records from across Europe and North America, and in dozens of other proxy archives. It represents one of the most abrupt climate changes of the entire Holocene, the geological epoch we are currently living in. Global temperatures dropped by several degrees within decades. The change was rapid enough to be clearly identifiable in annual ice layers, and its cause is now attributed, with fairly broad consensus, to the catastrophic drainage of proglacial lakes Agassiz and Ojibwe, the enormous bodies of meltwater that had been impounded against the retreating southern and eastern margins of the Laurentide ice sheet. Lake Agassiz, at its maximum, was the largest lake in the history of North America, possibly the largest lake in the history of the world during the last 20,000 years. It was not a natural feature in the way modern lakes are natural features. It was a meltwater lake, a body of water trapped between the retreating ice to the north and the higher ground of the continental interior to the south and west. At its greatest extent, Lake Agassiz covered a surface area of approximately 840,000 square kilometers, which is larger than all of the modern Great Lakes combined. It contained an enormous volume of fresh water. Estimates range widely because the lake changed dramatically in extent and depth over its lifetime, but at its maximum, the volume may have been comparable to or exceeding the volume of all of today's Great Lakes combined. This water was cold. It was fresh, and it sat on top of bedrock that was itself still rebounding from the weight of ice. The lake's drainage history is complex because as the ice retreated and the land rebounded, the outlets through which Agassiz drained shifted over time. At various points, it drained south into the Mississippi system, west into the Mackenzie system, and east toward the St. Lawrence. But around 8,200 years ago, based on the best current reconstruction, the ice dam that had been holding the lake back in the east, the remnant Laurentide ice between Hudson Bay and the Lake Agassiz Basin, collapsed, and perhaps as much as 163,000 cubic kilometers of cold, fresh water, some estimates run higher, drained catastrophically into Hudson Bay, and from there into the North Atlantic. The consequences of putting that much cold, fresh water into the North Atlantic in a geologically short time were severe, and they were felt not just in North America, but across the Northern Hemisphere. The Atlantic thermohaline circulation, the system of ocean currents that transports warm water from the tropics northward and drives the relatively mild climate of northwestern Europe, is sensitive to the salinity and temperature of surface water in the North Atlantic. When fresh water enters the North Atlantic in large volumes, it reduces the salinity and density of surface water, which disrupts the sinking of surface water that drives the circulation. The 8.2 kiloyear event appears to have caused a significant slowdown of this circulation, producing cooling across the North Atlantic region, drought in parts of Africa and the Middle East, and disruption of monsoon patterns across much of the tropics. The signal in the Greenland ice cores is stark. Temperature dropped, precipitation changed, and then, over the course of perhaps a century or two, the circulation recovered, the lake water that had entered the ocean mixed and was absorbed, and the climate stabilized again at Holocene conditions roughly similar to what they had been before. But during those few centuries, the world experienced something that anyone living through it would have found incomprehensible and terrifying, and people were living through it. The question of when humans first arrived in the Americas is a question that has been in active revision for the past 2 decades, and the revisions have been moving consistently in one direction, earlier. The Clovis first model, which held that the first people to enter the Americas arrived approximately 13,000 years ago via the Beringian land bridge and spread south through an ice-free corridor between the Laurentide and the Cordilleran ice sheets, has been substantially complicated by archaeological evidence from sites that predate Clovis culture. Monteverde in southern Chile, where Tom Dillahay's team documented unambiguous evidence of human occupation at 14,500 years before present, was among the first sites to force a serious reckoning with the Clovis first model. If people were in southern Chile 14,500 years ago, they had to have arrived in the Americas earlier than Clovis, because no one has proposed a mechanism by which people could have gotten from Beringia to southern Chile in the time it would take at realistic travel rates. The math does not work. The people had to have been here earlier, or they had to have arrived by a different route, or both. The coastal migration hypothesis, the idea that the first Americans followed the Pacific coast southward in watercraft, moving from island to island and headland to headland along what was then the ice-free Kelp Highway, a productive coastal environment stretching from the Alaskan coast down to the tip of Baja California, has gained significant support. The problem with testing this hypothesis directly is that the coastline of 15,000 years ago is now underwater. Sea level rise, since the end of the glacial maximum, has submerged the former coastline by anywhere from 60 to 130 meters, depending on location. Any camps left by coastal migrants along the route they traveled would now be on the sea floor. Archaeological survey of underwater sites is expensive, technically demanding, and rarely done. But the evidence from sites that are accessible on land has been accumulating. Cooper's Ferry in Idaho dates to approximately 16,000 years ago, based on multiple lines of evidence. Chiquihuite Cave in Mexico has produced evidence of human presence as far back as 26,000 years ago, though this date remains contested and some researchers are skeptical of the very early levels. Bluefish caves in the Yukon have yielded animal bones with cut marks that may date to as much as 24,000 years ago. The picture that is emerging is not a single wave of migration, but a more complex pattern of multiple entries, multiple routes, and a human presence in the Americas that extends considerably further back than the Clovis model allowed. What this means for understanding what happened when the Laurentide ice sheet collapsed is that the people who experienced it were not recent arrivals with a thin foothold in an unfamiliar landscape. Many of them, particularly those in areas south of the ice margin, had been in the Americas for thousands of years. They had adapted to the landscapes shaped by the presence of the ice sheet. They had developed subsistence strategies, social structures, and ecological knowledge tuned to conditions that included the periglacial environments at the ice margin, the vast grasslands of the glacial interior, where megafauna, including woolly mammoths, mastodons, giant ground sloths, giant bison, and horses, roamed in numbers that would be difficult to imagine today, and the complex river systems that drained meltwater across the continent. When the ice began to collapse in earnest, the world those people knew began to transform around them. And some of what it transformed into is recorded, faintly but persistently, in the oral traditions that researchers have only recently begun to treat as potentially valid archives of geological events. The oral traditions of indigenous peoples in North America contain accounts that, when examined carefully by researchers who are willing to take them seriously as data, describe events that correspond remarkably well to the geological record of deglaciation. The Anishinaabe traditions of the Great Lakes region contain accounts of a great water, a vast flooding of the land, a time when the waters came and reshaped the world. The traditions of peoples in the Pacific Northwest contain layered accounts of catastrophic flooding that some researchers have connected to the Missoula floods, the repeated catastrophic draining of a proglacial lake in Montana that sent walls of water across eastern Washington and into the Columbia River basin. The Stowe, Low people along the Fraser River in British Columbia have traditions that describe the land as it was when the ice was present and as it was when the ice retreated, traditions that encode geographic information about features that can be verified by modern geological survey. Researchers Patrick Nunn and Nicholas Reed, who have done systematic comparative work between indigenous oral traditions and geological evidence, have demonstrated, in peer-reviewed papers, that oral traditions can accurately encode geological information about sea level changes over periods of more than 7,000 years. Their methodology, which cross-references the specific geographical claims made in oral traditions with independent geological data, has produced results that are difficult to explain as coincidence. This is not mythology in the dismissive sense of the word. This is a form of knowledge transmission that researchers are increasingly recognizing as capable of preserving accurate empirical information across timeframes that would once have been considered impossible for oral tradition. The fidelity of oral transmission depends on the social and ceremonial structures surrounding it, on the degree to which the information is considered important enough to preserve with care, and on the oral tradition's internal mechanisms for detecting and correcting errors. Indigenous oral traditions that encode geological and ecological information about survival-relevant events, catastrophic floods, major changes in landscape, the disappearance of food sources, the transformation of seasonal patterns, had strong selection pressure to preserve that information accurately. Getting it wrong could mean making decisions based on false information about where water was, where the land was stable, where resources could be found. The traditions that survived are the ones that worked. Which brings us to an aspect of the Laurentide collapse that most accounts skip over entirely: the megafauna. The large animals that lived across North America during the last glacial maximum and into the early deglaciation period, are now gone. Mammoths, mastodons, ground sloths, giant beavers the size of modern black bears, short-faced bears taller than grizzlies at the shoulder, American horses, American camels, the dire wolf, the American lion, the American cheetah, the giant armadillo. All of them are gone. Their extinction, which took place roughly between 14,000 and 10,000 years ago, is one of the most studied and most contested questions in quaternary science. Two major hypotheses have dominated the debate for decades. The overkill hypothesis, associated most prominently with Paul Martin, which attributes the extinctions primarily to human hunting, as newly arrived people with advanced projectile weapons encountered megafauna that had no evolutionary experience with human hunters and were therefore behaviorally naive about the threat they posed. And the climate change hypothesis, which attributes the extinctions primarily to the rapid environmental transformation associated with deglaciation, the shift from cold, dry, glacial conditions to warm, moist, interglacial conditions, the replacement of the productive grasslands on which the megafauna depended with forests and wetlands, the disruption of seasonal patterns, the fragmentation of habitat. The current state of the debate is that neither hypothesis fully explains the pattern of extinctions on its own, and most researchers who have engaged seriously with the evidence have moved towards some form of combined explanation in which both human pressure and climate change contributed, with the relative importance of each varying by species, by region, and by timing. What is clear is that the extinction of North American megafauna was not gradual in geological terms, it was rapid, and it happened in a period that overlaps with both the final phases of Laurentide deglaciation and with evidence of human presence across the continent. The timing is uncomfortable. It is uncomfortable for researchers who want a clean, single-cause explanation, and it is uncomfortable for anyone who wants to tell a simple story about either the first Americans or about what climate change does to ecosystems. What happened to the landscapes those animals lived in when the ice retreated is worth understanding in detail, because it shapes everything that happened to the human societies that came after. The periglacial zone immediately south of the Laurentide, the area of tundra and permafrost and sparse vegetation that existed in the shadow of the ice sheet, supported a particular kind of ecosystem called the Mammoth Steppe or the Pleistocene Steppe. This was a cold, dry, productive grassland ecosystem that extended across vast areas of the glacially influenced landscape. It was not the lush forest and meadow landscape that now covers much of eastern Canada and the northeastern United States. It was windier, colder, drier, and remarkably productive in terms of the biomass of large grazing animals it supported. The key to its productivity was a combination of low winter snowpack, which allowed large animals to pour through to the grass beneath, and the abundance of grasses and sedges that grew rapidly during brief but intense Arctic summers. When the climate warmed and the ice retreated, this ecosystem began to disappear. Forests moved northward as temperatures rose. The productive grasslands contracted. The animals that had thrived on them found their habitat fragmenting and retreating. In the east, as the Laurentide retreated and exposed new land, the earliest vegetation to colonize the newly deglaciated terrain was sparse, tundra-like, and not particularly productive as a food base for large grazers. Behind that tundra, as soils developed and accumulated organic matter, more productive vegetation followed. But this succession took time. The newly exposed land behind the retreating ice margin was, for decades and centuries, a landscape of raw glacial till, exposed bedrock scoured clean by the ice, kettle ponds and bogs in the depressions left by stagnant ice blocks, and meltwater rivers braiding across outwash plains. Not a hospitable landscape for people or large animals, but not empty either, because the margins of that new landscape, where the fresh glacial terrain met the older established landscape to the south, created ecotonal zones of extraordinary ecological richness, places where different ecosystems overlapped and where resources of many different kinds were concentrated. Human societies at the margins of retreating glaciers were, in many documented cases around the world, highly successful. The same pattern can be seen in Scandinavia, where the retreat of the Scandinavian ice sheet was followed closely by human reoccupation of newly available terrain as soon as conditions allowed. In North America, The evidence for human presence in areas recently vacated by the Laurentide accumulates quickly once you know where to look and how to look for it. The problem is that much of the earliest post-glacial occupation of the newly deglaciated landscape in Canada is difficult to find archaeologically because the landscape itself was so dramatically transformed by the ice. The ice scoured the bedrock, mixed and moved the sediments, and left behind a terrain where any organic material from before the glaciation was simply gone, and any organic material from immediately after the glaciation was subject to the same dynamic forces of meltwater, permafrost, thaw, and landscape instability that were reshaping the entire terrain. This is one reason why the archaeological record of early post-glacial occupation in Canada is so sparse compared to areas further south that were not directly affected by the ice. It is not necessarily because people were not there. It is partly because the conditions for preserving organic material in the immediate post-glacial landscape were poor, and partly because relatively little systematic archaeological survey has been done in the areas most recently vacated by the ice in northern Canada, compared to the intensive survey work that has occurred in the more accessible and more extensively settled parts of the continent. There are researchers who have argued, based on this taphonomic logic, that the apparent scarcity of early post-glacial sites in northern Canada represents a bias in the archaeological record rather than a genuine absence of people. This argument is not universally accepted, but it is a serious methodological point about how we are reading the evidence we have. The communities that did occupy the areas south of the retreating Laurentide, in the period from roughly 16,000 to 10,000 years ago, were dealing with a landscape in constant transformation. River systems that had followed courses established by the pre-glacial terrain were being disrupted and rerouted by the new meltwater drainage patterns. Lakes were appearing where there had been none, filling basins scoured by the ice, and then draining or transforming as outlets were established, or as the land rebounded. The climate was changing not smoothly but in fits and starts, with periods of more rapid warming alternating with reversals and pauses. The Younger Dryas, which began approximately 12,900 years ago and lasted about 1,200 years, was one of the most dramatic of these reversals, a period in which temperatures in the North Atlantic region plunged back toward near-glacial conditions within a century or less, probably triggered by a reorganization of ocean circulation associated with a large influx of meltwater. The Younger Dryas is visible in the Greenland ice cores as clearly as a stop sign. Temperature dropped, dust increased, the ice accumulation rate changed, and then, at around 11,700 years ago, just as abruptly, the Younger Dryas ended. Temperatures in Greenland rose by approximately 10 degrees Celsius within a few decades. Ice cores preserve annual layers, and the transition at the end of the Younger Dryas is captured in those layers with a precision that leaves no ambiguity about how fast it happened. It happened fast. Human lifetimes fast, potentially within a single generation. And North America felt it. The societies that had adapted to Younger Dryas conditions were suddenly dealing with a different world again. The last major advance and then rapid retreat of the Laurentide in some sectors occurred during and after the Younger Dryas, as the climate oscillation created complex patterns of re-advance and retreat in different parts of the ice sheet simultaneously. The Younger Dryas saw the Laurentide margin stabilize, or even redvance slightly in some areas, while other sectors continued to retreat. The transition out of the Younger Dryas drove renewed rapid retreat across much of the ice sheet margin, contributing additional meltwater to the ocean and to the growing network of proglacial lakes. The proglacial lakes were not simply overflow ponds. They were active, dynamic systems that shaped the landscape and the climate of the surrounding region in ways that go beyond simply being large bodies of water. Lake Agassiz, at its various stages, had a surface area and depth that gave it a significant moderating effect on the regional climate. Large water bodies store heat in summer and release it in winter, buffering the temperatures of surrounding areas. The presence of Agassiz over the interior of the continent created a distinct regional climate regime that influenced precipitation, wind patterns, and the distribution of ecosystems around it. Communities living near the shores of Agassiz were living in a climate envelope different from what was present in the surrounding region, and that climate envelope was itself shifting as the lake expanded and contracted over the centuries of its existence. The shorelines of Lake Agassiz, The raised beaches and wave-cut terraces that mark its various stands are still visible in the landscape of the Canadian prairies, Manitoba, Saskatchewan, and beyond. They are among the most dramatic geomorphological features of the interior of the continent, vast flat terraces of lake sediment stretching for hundreds of kilometers, the remnants of a lake bottom that is now some of the most productive agricultural land in the world. The Red River Valley of Manitoba and Minnesota sits in the floor of former Lake Agassiz. The extraordinary flatness of that landscape, which makes it ideal for farming and which can feel almost surreal to a visitor accustomed to more varied topography, is a direct inheritance of the lake that sat there for thousands of years, depositing fine sediments from the meltwater streams that fed it. Every flat field in that valley is former lake bed. The land is Agassiz, and buried within that land, in the sediments and organics that were deposited on the lake floor and around its margins, are the records of what happened to the lake and to the people who lived near it. Human occupation of the shores of Lake Agassiz is documented archaeologically, though the record is complicated by the fact that the lake's shoreline moved dramatically over time, and some former shore environments are now either submerged under younger lake sediments or exposed in locations that are not obvious to survey without knowing the paleotopography of the lake basin. The Ojibwe and Cree and other Algonquian-speaking peoples of the region have oral traditions that encode the memory of great water covering the land. Traditions that speak of a time when the world was different, when the water was everywhere and the land was not as it is now. These traditions have been collected and studied by ethnographers and anthropologists for more than a century, and the recent turn toward taking oral traditions seriously as potential archives of genuine geological memory has prompted some researchers to revisit them with new analytical frameworks. The question is not whether these traditions describe Lake Agassiz directly, since the lake disappeared more than 8,000 years ago, but whether they preserve, in transformed and mythologized form, information about landscape conditions that was transmitted through more than 300 generations of storytelling. The evidence that this kind of transmission can preserve genuine geological information is now strong enough that the dismissal of such traditions as merely symbolic has become difficult to sustain without engaging seriously with the project. Methodological arguments. The Cree and Ojibwe traditions of the flooding of the world, of a great water that covered the land and from which the land eventually emerged, echo across a surprisingly wide geographic range. They are not identical traditions, because they have been adapted and localized by different communities over the centuries since the geological events they may encode. But the structural similarity of water covering land, the emergence of new land, the transformation of the world as it was known into the world as it now exists, those elements recur with a consistency that researchers like Nunn and Reed find more consistent with encoding of real geological events than with independent mythological invention. The comparison with indigenous traditions from Australia, where similar methodological work has demonstrated that oral traditions can encode accurate information about sea level changes over periods of 7,000 years, is instructive. The mechanisms are different, the landscapes are different, the cultures are different, but the underlying principle that human communities with strong oral transmission systems can preserve accurate landscape information across very long timescales appears to be robust. The drainage of Lake Agassiz into Hudson Bay at approximately 8,200 years ago, the event that triggered the 8.2 kiloyear cold event, would have been experienced in real time by the communities living near the lake's eastern margin. The drainage was not instantaneous. It appears to have occurred over a period of years to decades, rather than in a single catastrophic moment. Though the geological distinction between years and decades is somewhat academic, when you are the person watching the water begin to drop. What the people living near the eastern shore of Agassiz would have seen was the lake level declining, perhaps rapidly, as the ice dam to the east failed and the water found a new outlet. The pace of that decline is estimated by some researchers to have been as fast as several meters per year during the most acute phase of drainage. For communities whose settlements and subsistence activities were calibrated to the existing lakeshore environment, this would have been a disaster. Food sources associated with particular lake depths and shore environments would have changed or disappeared. Canoe routes would have become unnavigable. Spawning grounds for fish would have shifted. The geography of the world as they knew it would have been transforming faster than they could track it. And then the cold. Because the cold came across the northern hemisphere as the drainage water entered the North Atlantic and disrupted the thermohaline circulation. How quickly the cold was felt on the shores of the newly draining Agassiz Basin is a matter that the geological record cannot resolve with enough precision to say whether it came within years or decades of the drainage beginning. But it came, and it persisted for perhaps 1 to 2 centuries before the ocean circulation recovered. The people who had been living at the margins of the greatest lake in North American history found themselves dealing simultaneously with the disappearance of that lake and with a climate reversal that would have disrupted plant, phenology, animal migration patterns, fish spawning, and all of the seasonal ecological rhythms on which their subsistence systems depended. This is the story that is not in the textbooks. Not because it is speculative or uncertain in its broad outlines, because the geological evidence for what happened is solid. The 8.2 kiloyear event is one of the best documented climate events in the Holocene record, and the connection between Lake Agassiz drainage and the thermohaline disruption is the dominant explanation in the peer-reviewed literature. The story is not in the textbooks, because textbook history begins with writing, and writing did not exist in North America 8,000 years ago. The people who lived through this were not writing it down. They were surviving it, or not surviving it, and passing on what they knew through oral tradition and material culture and the accumulated adaptive knowledge of communities that had to figure out, in real time, how to deal with a world that was changing faster than any preceding generation had seen. What happened to those communities over the centuries following the 8.2 kiloyear event is recorded, partially and imperfectly, in the archaeological record of the Archaic period. The term archaic, as used in North American archaeology, refers to the period roughly between 10,000 and 3,000 years ago, after the Paleo-Indian period characterized by Clovis and related projectile point traditions and the megafauna hunting economy, and before the widespread adoption of agriculture and the development of complex sedentary societies in most parts of the continent. The Archaic is often described in introductory accounts as a period of adaptation and diversification, which is accurate, but undersells how dramatic that diversification was, and how much it tells us about the resilience and creativity of the communities involved. What the Archaic represents, across its more than 7,000 years of duration, is the development by human communities across North America of sophisticated, regionally adapted subsistence systems that took advantage of the specific ecological conditions of each region after deglaciation had transformed the landscape. In the Great Lakes region, where the drainage of glacial lakes had created one of the world's most complex freshwater ecosystems, communities developed highly specialized fishing economies. The variety of fish species available in the post-glacial Great Lakes was extraordinary, and the people who lived along these shores developed fishing technologies, including nets, weirs, hooks, and specialized watercraft that allowed them to exploit this resource base with great efficiency. The evidence for Archaic period fishing in the Great Lakes region includes preserved fishbone assemblages that show a remarkable sophistication in species selection and processing, the remains of weirs and traps in some locations where preservation conditions have been favorable, and the abundance and health of human skeletal remains that show diets rich in high-quality protein. These were not marginal populations struggling to survive at the edge of an unfamiliar landscape. They were prosperous communities that had developed deep knowledge of a specific environment and were exploiting it effectively. In the boreal forest zone that developed across the interior of Canada, as the Laurentide retreated and soils accumulated and tree communities established themselves, communities developed economies centered on the hunting of caribou, moose, and woodland bison, supplemented by freshwater fishing and the harvesting of a wide variety of plant foods and small game. The boreal forest is often described as a challenging environment for human habitation because of its low productivity per unit area and the wide-ranging nature of the animals it supports. But communities adapted to it developed mobility strategies and social structures that allowed them to follow resources across large territories while maintaining the social networks necessary for sharing information, exchanging mates, and cooperating in large-scale hunts. The vast territories over which some Archaic and later woodland period communities ranged are visible in the distribution of certain types of stone, trade goods, and stylistic similarities in material culture across distances of hundreds of kilometers. The coastal areas of eastern and Atlantic Canada, including what is now the Maritimes, southern Labrador, and Newfoundland, show evidence of archaic period occupation that is notable for its sophistication and for the evidence of long-distance maritime connections. The maritime archaic tradition, which began approximately 8 to 9,000 years ago and continued for several thousand years, is documented at sites along the coasts of Labrador and Newfoundland, and represents one of the earliest, well-documented examples of a marine-adapted economy in North America. Maritime archaic people hunted sea mammals including seals, walrus, and possibly whales, fished in coastal waters and rivers, and traveled by boat along coastlines and possibly across open water. The presence of maritime archaic artifacts in locations that can only be reached by sea travel indicates a maritime technology and navigational capability that was more sophisticated than the term archaic might suggest to someone unfamiliar with what archaic actually means in this context. One of the most remarkable aspects of the maritime archaic tradition is the burial complex associated with it, documented most extensively at the site of Port O'Shoy on the northwestern coast of Newfoundland. Maritime archaic burials at Port O'Shoy and related sites contain elaborate assemblages of grave goods, including carved bone and antler objects, pendants made from the teeth of large marine mammals, tools made from non-local stones obtained through long-distance exchange, and ochre, always ochre, the red mineral pigment that appears in burial contexts across such a vast geographic and temporal range that its recurrence in contexts from Pleistocene Africa to archaic North America has prompted serious discussion about whether its use in mortuary ritual reflects a pan-human tendency or a specific cultural tradition with deep roots. The maritime archaic graves show communities that had developed complex ceremonial life, beliefs about death and what followed it, and social structures capable of producing and maintaining the elaboration of material culture that the grave goods represent. These were not simple, primitive people. They were fully human in every relevant sense, with rich cultural lives and sophisticated understanding of the world they inhabited. The relationship between these archaic period communities and the ongoing environmental changes associated with the last phases of Laurentide deglaciation is a question that researchers are only beginning to address systematically. The land was still rising in many parts of Atlantic Canada and the Maritimes during the maritime archaic period. Former coastal sites were being exposed by isostatic rebound in some areas, while being inundated by rising sea level in others, because the two processes were occurring simultaneously, but at different rates in different locations. The geography of coastlines and river mouths and bay configurations was not fixed during this period. It was changing, sometimes fast enough to be noticeable within a human lifetime. Communities that oriented their subsistence strategies around particular coastal configurations or river mouth fish runs would have had to adapt as those configurations changed. The archaeological record of the maritime archaic contains evidence of communities doing exactly this, relocating and adapting their settlement patterns as the landscape changed beneath and around them. Further west, the retreat of the Cordilleran ice sheet, the ice mass that covered the mountains and interior of British Columbia and extended into Washington, Idaho, and Montana, created a different but equally dramatic landscape transformation. The Cordilleran and the Laurentide had been in contact, their margins meeting somewhere in the interior of what is now Alberta and British Columbia, creating the barrier that had blocked a southern route from Beringia for much of the glacial maximum. As both ice sheets retreated, a corridor opened between them. The timing of when this ice-free corridor became actually passable, meaning ecologically productive enough to support people and the animals they depended on, is a subject of active research and ongoing debate. Early models assumed the corridor opened relatively quickly after the initial retreat of the ice margins. More recent work, examining the ecological evidence of what was actually growing in the corridor and when, has suggested that the corridor did not become genuinely habitable until around 13 to 14,000 years ago at the earliest, and that the productive coastal route may have been the primary path for initial human entry into the Americas rather than the ice-free corridor. The landscape of the Cordilleran deglaciation was shaped by a phenomenon that rivals the Lake Agassiz drainage for sheer spectacle, though it predates it considerably. The Missoula floods, the repeated catastrophic outburst floods that occurred as the ice lobe damming glacial Lake Missoula in Montana repeatedly failed and reformed, are among the most dramatic flood events documented in the geological record of the Holocene and Late Pleistocene. At its maximum, Lake Missoula contained roughly 2,000 cubic kilometers of water, comparable in volume to Lake Erie and Lake Ontario combined. When the ice dam failed, which it did repeatedly, perhaps dozens to hundreds of times over a period of roughly 2,000 years, the lake drained in a matter of days to weeks. The floodwaters crossed eastern Washington at speeds estimated at up to 90 kilometers per hour, carved the channeled scablands, eroded coulees and potholes into the basalt plateau, and deposited debris, including boulders weighing hundreds of tons, at locations hundreds of kilometers from their source. The scale of erosion accomplished by the Missoula floods, which the geologist J. Harlan Bretz documented and argued for in the 1920s, to the initial skepticism of colleagues who could not believe that conventional geological processes had not produced the scabland topography, was recognized only gradually as the correct explanation for one of the most unusual landscapes in North America. The Stowe, Low people of the Fraser River Basin have traditions that speak of catastrophic flooding. So do the Yakima and other plateau peoples of eastern Washington. These traditions, examined in light of the Missoula floods research, have been argued by some researchers to encode memory of the actual events, transmitted through oral tradition across the 10 to 13,000 years since the last major floods. This claim is contested, and the question of whether oral traditions can reliably encode information over that timescale without significant distortion is not resolved. But the methodological discussion it has prompted about how to evaluate the potential geological accuracy of indigenous oral traditions is one of the more interesting conversations currently happening at the intersection of geology, archaeology, and indigenous studies. The broader context for these conversations is a growing recognition that the peoples of the Americas, in the period from the end of the last glacial maximum to the beginning of the historical period as European contact defines it, were not passive observers of the landscape around them. They were active managers of it, in ways and to degrees that the traditional narrative of wilderness-dwelling hunter-gatherers does not capture. The evidence for pre-Columbian landscape management in North America has been accumulating for decades, and it has reached a point where the old paradigm of indigenous peoples living lightly on a wilderness that was essentially unmodified by human action is no longer defensible as a description of most of the continent for most of the period in question. The controlled burning practices of many indigenous nations, documented in historical sources and still practiced in some areas today, produced landscapes that looked natural to European observers, but were actually managed environments, shaped by millennia of deliberate fire regimes to maximize the productivity of particular plant communities for human use, and to create and maintain the habitat conditions that supported the game animals that people depended on. The grasslands of the Great Plains were maintained in part by fire as well as by bison grazing. The open woodlands of much of eastern North America were products of burning as well as of natural fire regimes. The berry patches and meadows and game-rich forest edges that European explorers described as the natural bounty of a virgin continent were in many cases the products of long-term human management. This matters for understanding the Laurentide collapse because it means that what the ice sheet's retreat produced, in terms of landscape, was not a blank canvas that humans simply occupied. It was a landscape that, over the thousands of years following deglaciation, was progressively shaped by the communities that moved into and through it. The boreal forest that now covers much of Canada is not exactly what it would be in the absence of 10,000 years of human management. The wetlands and the river systems and the coastal environments are all modified to some degree by long-term human use and management. When Europeans arrived in the Americas, beginning in the late 15th century, and looked at what they described as untouched wilderness, they were looking at a landscape that had been shaped by human hands for 10,000 years. That is the landscape that followed from the collapse of the Laurentide ice sheet. The Hudson Bay drainage basin, the vast watershed that collects water from nearly 4 million square kilometers of northern Canada and funnels it into Hudson Bay and ultimately to the North Atlantic, carries a particular historical weight in the story of the Laurentide collapse. Hudson Bay itself, as mentioned earlier, was the site of the Laurentide's central dome. The ice there was the last to go, persisting long after the margins of the sheet had retreated. The final opening of Hudson Bay to the sea, as the last remnant ice melted and the bay became connected to the open ocean, is estimated to have occurred sometime around 8 to 8.5 thousand years ago, approximately coinciding with, and perhaps contributing to, the drainage of the last of the Agassiz-Ojibwe system. The proglacial lakes that had occupied the Hudson Bay Basin itself, trapped between the retreating ice and the bedrock exposed by isostatic rebound, drained as outlets opened. The Tyrrell Sea, as it is sometimes called, the shallow post-glacial sea that extended into the Hudson Bay Basin and beyond it into the Fox Basin and Hudson Strait in the immediate period after the ice cleared, was not quite the same body of water as modern Hudson Bay. It was larger, extending into areas that are now land, because the land had not yet rebounded from the weight of the ice. The shorelines of the Tyrrell Sea, visible today as raised beaches and marine sediments well above modern sea level in places around Hudson Bay, mark the extent of that post-glacial marine incursion. The raising of the land around Hudson Bay has continued to the present day. As noted earlier, this ongoing rebound is not merely of academic interest. It is measurable by GPS. It affects the hydrology and ecology of the region, and it is a physical manifestation of the continuing geological response to an event that happened 8,000 years ago. The land is still moving because of what the ice did. The ice shaped the land in its presence and is still shaping it in its absence. The Cree and Inuit communities that live around Hudson Bay today live on land that is literally rising beneath their feet, land whose shorelines have changed measurably within living memory, a physical connection between the present and the glacial past that is unique in the world. The communities around Hudson Bay in the pre-contact period were among the most sophisticated cold environment societies that have ever existed. The Dorset culture, which occupied the Arctic and subarctic regions of Canada from approximately 3,000 years ago to around 1,000 years ago, developed technologies for living in some of the harshest environments on Earth. Their toolkits, which have been preserved in remarkable detail by the cold conditions that retard organic decay, show a mastery of materials and techniques that allowed them to survive and thrive in environments where temperatures can drop to -50 degrees Celsius in winter and where the growing season is measured in weeks rather than months. The Dorset were eventually replaced by the Thule people, the ancestors of modern Inuit, who expanded eastward from Alaska approximately 1,000 years ago and brought with them a different set of technologies centered on the hunting of large marine mammals, particularly bowhead whales, from kayaks and umiaks. The transition from Dorset to Thule is one of the more archaeologically visible cultural transitions in the Arctic record, and its causes are debated, but the context of climate change during the medieval warm period and the Little Ice Age has been invoked as a contributing factor. Before either the Dorset or the Thule, the earlier inhabitants of the Hudson Bay region were dealing with the aftermath of the Laurentide collapse and the transformation of the landscape it produced. The shield archaic tradition of the Canadian Shield, one of the earliest archaeological cultures documented in the boreal forest region, dates back approximately 7,000 years in some areas, representing communities that moved into the newly deglaciated terrain of the Canadian Shield as it became habitable. These communities left behind a sparse archaeological record, partly because they were small and mobile, and partly because the preservation conditions in the boreal environment are not favorable for most organic materials. But what survives suggests communities that were hunting caribou and moose across vast territories, fishing the lakes and rivers that had formed in the depressions scoured by the ice, and using stone from quarries, sometimes hundreds of kilometers, from where the tools made from that stone are found. The distances imply travel, trade, and social networks extending across the landscape. The copper-using cultures of the Great Lakes region represent one of the most remarkable early metallurgical traditions in the world. The native copper deposits of the Lake Superior region, particularly around the Keweenaw Peninsula of what is now Michigan, had been recognized and exploited by indigenous peoples for at least 7,000 years, possibly longer. The Old Copper Complex, as archaeologists call it, produced a remarkable variety of copper implements, including spear points, knives, awls, and ornamental objects, using techniques of cold hammering and annealing that produced forms of astonishing sophistication. The geographic distribution of old copper objects, which have been found across a huge area of the upper Midwest and Great Lakes region, indicates long-distance exchange networks of considerable antiquity. Copper from Lake Superior traveled hundreds of kilometers from its source, passing through networks of exchange that connected communities across the post-glacial landscape. The existence of these exchange networks, which are documented not just for copper, but for a range of materials, including specific types of chert, obsidian from western sources, marine shell from Gulf Coast and Atlantic sources, and various other non-local materials, indicates that the post-glacial communities of North America were not isolated pockets of people, each coping independently with the landscape changes around them. They were connected. Information about where resources could be found, about what was happening to the landscape, about the movement of game animals and the timing of fish runs, moved through those networks. When the climate changed, when floods came, when the land transformed, that information moved too. The communities most likely to survive major environmental disruptions were not necessarily the ones with the best immediate adaptive strategies. They were the ones embedded in the widest and most robust social networks, because networks could buffer individual communities against local failures. This is a principle that appears in the archaeological record repeatedly, not just in North America but globally. Communities with strong long-distance connections tended to persist through environmental crises better than isolated communities, even when the isolated communities had apparently superior local adaptations. The reason is straightforward. Any local environment can fail. Any local resource can disappear. But a network that spans multiple environments and multiple resource bases provides options that no single community can provide for itself. And the networks that connected post-glacial communities in North America were extensive, reaching across the landscape that had been shaped by the Laurentide collapse and threading through the transformed geography that followed the ice. The question of what happened to those networks, and to the communities within them, in the period between the final deglaciation and the arrival of Europeans, is a question that the archaeological record answers only partially. The woodland period traditions that developed across much of eastern North America, beginning around 3,000 years ago, show the emergence of more complex social structures, including ceremonial mound building, elaborate mortuary practices, long-distance exchange in luxury goods, and in some areas, the beginning of agricultural production. The Hopewell tradition, which reached its florescence between roughly 2,000 and 1,600 years ago in the Ohio Valley and spread its ceremonial influence across much of eastern North America, represents one of the most expansive and sophisticated pre-Columbian cultural traditions on the continent, and it was built on foundations of post-glacial, ecological, and social development that stretch back thousands of years. The earthworks of the Hopewell tradition, some of which survive today as remarkable monuments to the organizational capacity of their builders, are the visible remainder of a cultural tradition whose full extent and complexity we are still in the process of understanding. The earthworks of the Ohio Hopewell, centered particularly around the Scioto River Valley, include geometric enclosures of extraordinary precision. The Newark earthworks, in Licking County, Ohio, the largest complex of geometric earthworks in the world, covers an area of more than 40 square kilometers and includes circles, octagons, and connecting walls arranged in a configuration that preserves, with considerable astronomical precision, the 18.6-year cycle of the Moon's maximum and minimum rise and set points. This precision was not accidental. Researchers Ray Hively and Robert Horn demonstrated in papers published in the 1980s and confirmed by subsequent work that the alignment of the Newark octagon's principal axis with the maximum northern moonrise is accurate too, within a fraction of a degree, and that a single alignment that precise could not be the result of chance, but rather reflects deliberate design based on careful and extended observation of the moon's movements. Building something that encodes the 18.6-year lunar cycle implies watching the moon long enough to know the cycle, which implies a tradition of lunar observation extending back considerably before the construction of the earthworks themselves. This tradition of careful observation of the sky and the encoding of that observation in material structures that persist and can be used to perpetuate the observational tradition across generations connects the Hopewell to a wider pattern of astronomical sophistication in pre-Columbian North America that researchers have been documenting with increasing systematicity over the past several decades. The medicine wheels of the northern plains, circular arrangements of stones with spokes radiating from a central cairn, have been argued to encode solstice, sunrise alignments, and other astronomical information. Bighorn Medicine Wheel in Wyoming, the most studied of these structures, sits at an elevation above 3,000 meters and has spokes aligned with the summer solstice sunrise and with the heliacal rising of several important stars. The structural parallels with Stonehenge in Britain are genuine, and they reflect not cultural contact, but the same human impulse to mark the movements of the sky in stone, an impulse that appears independently across many cultures and times. The stone alignments of the northern plains were not built by people who needed an astronomical calendar to survive. They were built by people for whom the sky was cosmologically significant, for whom the movements of celestial bodies encoded meaning about the proper order of the world and the human place within it. The cosmological traditions of the Plains nations, many of which have been documented through the work of researchers working in collaboration with indigenous communities, reflect this astronomical sophistication. The Blackfoot tradition of sky knowledge, for example, encodes detailed information about the positions and movements of stars, the use of stellar risings and settings to mark seasonal transitions relevant to their subsistence calendar, and the mythological significance of specific celestial configurations. This is not primitive stargazing. It is a systematic tradition of observation and interpretation that has been maintained and refined over a period spanning the entire post-glacial history of plains habitation. The connection between this astronomical tradition and the geological story of the Laurentide collapse is indirect but not irrelevant. The people who built the medicine wheels and maintained the sky knowledge traditions were the descendants, cultural and probably biological, of communities that had witnessed the transformation of the landscape from glacial to post-glacial conditions. The deep time perspective encoded in many indigenous traditions, the sense that the world has been through transformations before, that the land has different faces across vast spans of time, that the present configuration of the landscape is not the only one it has ever had. That perspective may have roots in the genuine collective memory of a people whose ancestors watched the ice retreat and the world change. It is not possible to verify this claim with the same confidence as a geological measurement, but it is also not possible to dismiss it without engaging seriously with what we now know about the capacity of oral traditions to encode genuine historical and geological information. The landscape that the retreating Laurentide produced in Western Canada, across what is now Alberta and Saskatchewan and into the Northwest Territories, has its own distinctive character and its own archaeological story. The parkland transition zone between the boreal forest to the north and the grasslands to the south was, and remains, one of the most ecologically diverse and productive landscapes in North America. It was also the zone through which bison herds moved in their seasonal migrations, and it was the zone that supported some of the densest pre-contact human populations in Western Canada. The head-smashed-in buffalo jump in southern Alberta, now a UNESCO World Heritage Site, documents the use of a bison hunting technique at that location extending back approximately 6,000 years, with evidence suggesting that the site and the surrounding landscape feature that makes it effective, a naturally occurring gathering slope that channels bison toward a cliff edge, were being used before that. 6,000 years of use at a single location is itself a statement about the sophistication of the communities involved. Understanding a landscape well enough to recognize that a particular topographic configuration can be made to function as a hunting facility, designing and maintaining the drive lanes of stone cairns and brush fences that direct the bison toward the jump, coordinating the large numbers of people necessary to drive the herds effectively, all of that represents a sophisticated tradition of land knowledge and social organization that is continuous with the broader post-glacial story of how human communities in North America adapted to and shaped the landscape that emerged from beneath the ice. The stone cairn systems of the southern Alberta uplands, some of which extend for many kilometers across the landscape, have been the subject of archaeological study that is still ongoing. These systems, which include the drive lanes associated with bison jumps, but also include other configurations whose purpose is less immediately obvious, appear in some cases to predate the documentary record of any particular cultural tradition. The Majorville Cairn, a large stone cairn at the center of a medicine wheel complex on a hilltop in the Bow River Valley of Alberta, has been dated on the basis of artifacts and stratigraphy within the cairn to approximately 5,000 years ago at its earliest definite use, with some evidence suggesting a longer history. This makes it one of the oldest medicine wheel complexes in North America, predating Stonehenge and the Egyptian Old Kingdom, and many of the monuments that tend to get discussed when pre-literate societies' astronomical sophistication is mentioned. The Majorville complex was used and modified continuously for thousands of years, accumulating layers of offerings and structural changes that document a tradition of use spanning the entire post-glacial period of intensive human occupation of the southern Alberta grasslands. The grasslands themselves are a product of the post-glacial climate, though they have older roots. The short grass prairie of the southern plains and the mixed grass prairie further north developed over the past 10,000 years as the glacial climate that had supported the Mammoth Steppe gave way to warmer, drier interglacial conditions. The bison, which had been present in North America during the glacial period, in forms that were somewhat different from the modern plains bison, survived the megafaunal extinctions and expanded dramatically in the warmer, drier post-glacial grasslands. By the time European observers first documented the bison herds of the Great Plains, the animals numbered in the tens of millions, possibly more. This extraordinary abundance was the product of a specific ecosystem configuration that had developed over the post-glacial period in the absence of the megafaunal competitors that had been lost to extinction, and in some respects in concert with the human management practices of the communities that depended on bison as their primary food source. The relationship between human hunting and bison population dynamics on the Great Plains is one that researchers have studied from multiple angles, and the emerging picture is not of simple predator-prey dynamics, but of a more complex relationship in which human hunting behavior and bison herd dynamics co-evolved over millennia. The introduction of the horse to the Great Plains, which began in the 17th century as horses escaped from or were traded from Spanish settlements in the southwest, transformed this relationship dramatically. But the horse was itself a return, in a sense. Horses had evolved in North America and been present on the continent until their extinction approximately 11,000 years ago as part of the broader megafaunal collapse at the end of the Pleistocene. The return of the horse to the plains, in the form of domesticated descendants of horses that had gone to Eurasia via Beringia and been domesticated there, was one of the more remarkable ironies of the contact period. The people who adopted the horse-based buffalo hunting economy of the historic plains nations were not inventing a new way of life. They were adapting a very old way of life, one built on the hunting of large grazing animals in the post-glacial grassland, to a new technology that transformed the scale and efficiency with which that hunting could be conducted. The North, the truly high north of the Canadian Arctic, tells a different version of the post-Laurentide story. The areas north of the tree line, which approximate the northern limit of the Laurentide's influence on the present landscape, were deglaciated later in some areas and experienced a different trajectory of ecological development. The Arctic and subarctic environments that developed after the ice retreated supported distinctly different human adaptations than those of the boreal and parkland zones to the south. The first people to move into the Canadian Arctic following deglaciation, the Paleo-Eskimo peoples whose artifacts are found at sites across the Arctic coast and islands, faced a landscape without the forest resources that subarctic hunters relied on. They developed technologies adapted to open tundra and sea ice environments, using driftwood and sea mammal bones and ivory rather than forest timber for construction, hunting seals and walrus and muskox and caribou rather than the forest-dependent animals of the south, and developing a suite of cold-weather technologies, including the lamp-burning sea mammal oil for heat and light, that allowed them to survive in conditions that would kill unequipped modern humans very quickly. The sequence of cultures in the Canadian Arctic, from the earliest pre-Dorset through the Dorset to the Thule to the modern Inuit, represents one of the most sustained and sophisticated traditions of cold environment adaptation that humans have ever produced. Each stage of this sequence represents not a replacement of one population by an entirely different one, but an evolution and transformation of technology and culture in response to changing environmental conditions, including the climate shifts of the last 3,000 to 4,000 years that produced alternating warm and cold phases in the Arctic. The medieval warm period, from roughly 900 to 1200 CE, appears to have been a significant factor in the expansion of the Thule people eastward from Alaska, as warmer conditions facilitated travel across previously ice-choked waters and may have affected the distribution and behavior of the bowhead whales that were central to Thule's subsistence. The subsequent cooling of the Little Ice Age, from roughly 13 to 1800 CE, created different challenges and opportunities, affecting sea ice extent and persistence, and thereby the conditions for sea mammal hunting. The story of the Laurentide collapse and its aftermath is therefore not simply a geological story, though the geology is remarkable. It is also a human story, the story of how communities adapted to conditions of change that operated on multiple timescales simultaneously, from the geological to the seasonal, and how the knowledge required to survive those changes was accumulated, encoded, and transmitted across the generations. It is a story that the conventional historical record, which begins with writing and favors literate civilizations, has systematically undercounted and undervalued. The people who managed the post-Laurentide landscape of North America for 10,000 years before European contact were not primitive forerunners of civilization. They were the inheritors and continuators of a tradition of ecological knowledge and social sophistication that began in North America when the first people looked at a landscape emerging from beneath the ice and began the long work of understanding it. There is a specific site in northern Quebec that deserves attention in the context of this story, because it represents one of the more striking examples of the kind of evidence that forces a revision of conventional assumptions. The Paleoeskimo site at Tayara on Kikiktaluk Island in Hudson Bay, excavated by researchers over multiple seasons, has produced evidence of sophisticated cold environment adaptation extending back more than 4,000 years. But it is the broader survey work in the Hudson Bay region that has produced results suggesting that the human occupation of the newly deglaciated terrain around Hudson Bay began earlier than the textbook reconstruction would predict. The challenge of finding these early sites is compounded by the fact that the coastline around Hudson Bay has been rising for 8,000 years, meaning that sites occupied when the bay first opened are now either far inland, on raised beaches above the modern shore, or are covered by the sediments of subsequent occupations and environmental change. Survey of these raised beaches in some parts of Hudson Bay has found evidence of occupation extending back several thousand years, with some locations showing human use beginning very shortly after the area became habitable following deglaciation. Very shortly, in this context, is a relative term. It means within a few centuries of conditions becoming minimally adequate for human occupation, which itself says something about how quickly people moved into newly available terrain. The research on early occupation of the Hudson Bay region is ongoing, and the picture it presents is still incomplete. But what is emerging is consistent with a broader pattern that the post-Laurentide story presents across North America. The landscape did not sit empty waiting to be discovered. As soon as conditions allowed, people moved in. They came from the south, along river corridors opened by meltwater drainage. They came from the east, along coastlines exposed by isostatic rebound and sea level dynamics. They came from the west, along the margins of the retreating Cordilleran ice. And they brought with them the accumulated knowledge of communities that had been navigating changing landscapes for thousands of years. Communities descended from people who had watched the ice advance and had waited and adapted and ultimately come through the other side. The voices of those communities, preserved in oral traditions that researchers are now taking seriously in new ways, speak to events and conditions that the geological record confirms. The great water that covered the land, the time when the world was different, the catastrophic floods, the cold that came unexpectedly, the animals that disappeared, the new landscapes that emerged from beneath retreating ice. These are not myths in the sense of being untrue. They are histories encoded in forms that served the communities that preserved them, across timeframes that dwarf anything in the written historical record. The challenge now is to develop the methodological tools to read them with the same critical care that we apply to any other historical source. The geological story of the Laurentide ice sheet collapse is, in the end, a story about change at scales that are difficult to hold in the mind simultaneously. The individual and the geological, the human lifetime and the 10,000 years. The experience of a community watching a lake drain and a climate shift, and the measurement of that event in ice cores and coral reefs and deep-sea sediment thousands of kilometers away. All of these are part of the same story. The 3 kilometers of ice that once sat over Canada, pressing the bedrock down and holding the continent in a cold grip that lasted 20,000 years, is still present in the landscape it left behind, in the lakes and rivers and wetlands of the boreal zone, in the flat fields of former lake beds, in the raised beaches of Hudson Bay, in the rebound that is still lifting the land, centimeter by centimeter, back toward where it was before the ice came, and in the traditions of the people whose ancestors witnessed the ice and survived it, whose knowledge of what the land can do and has done is encoded in the stories that they are still telling. What happened to the Laurentide ice sheet is not a simple story of gradual melting. The evidence for rapid events, catastrophic drainages, abrupt climate reversals, and the complex interplay of ice dynamics, ocean circulation, and the global climate system tells a more dramatic story. And within that drama, the human communities that experienced it, that adapted to conditions that changed faster than any preceding generation had encountered, that maintained and transmitted knowledge of what the land had been and what it had done, were not passive observers. They were participants in one of the most significant environmental transformations in the history of the continent, and the tradition of landscape knowledge and ecological management that they built on the post-glacial foundation is part of the heritage of every person alive today in North America. The ice is gone, the land is still rising, the traditions are still speaking, and researchers are still listening. There is one more dimension to this story that tends to be left out of both the geological accounts and the cultural ones, and it connects the deep past to something that researchers are paying close attention to right now. The Laurentide ice sheet, at its maximum, stored so much water that its melting contributed roughly 70 to 90 meters to the global sea level rise that occurred between the last glacial maximum and today. The additional meltwater from the Cordilleran ice sheet, from the Scandinavian ice sheet, from smaller ice caps around the world, added more. Modern sea level is roughly 120 meters higher than it was at the glacial maximum, and virtually all of that difference is because ice that once sat on land is now in the ocean. The coastal landscapes of the world are fundamentally different because of what happened to ice sheets over the past 20,000 years. Coastlines that were above water when the ice was at its maximum are now submerged. The continental shelves of the world are flooded landscapes that people once walked across. Off the coast of eastern Canada, the Grand Banks of Newfoundland, one of the world's most productive fishing grounds, sits on a submerged continental shelf that was largely exposed during the last glacial maximum. The maritime archaic people and their predecessors were fishing from shores that are now 40 to 60 meters underwater in many areas. Their coastal camps, their fish weirs, their middens full of shells and fish bones are on the sea floor. The chance of finding them is small but not zero, and as underwater archaeological techniques improve and as interest in the deep history of the continent grows, the prospect of recovering evidence from those drowned landscapes becomes more realistic. The question of what happened on the coast of eastern Canada in the period between the end of the last glacial maximum and the beginning of the period from which we have substantial archaeological evidence is partly a question whose answer is sitting on the sea floor. In the western interior of the continent, the fate of Lake Agassiz's bed tells a different story. The lake drained, the land rebounded, and what was once lake bed became prairie. The soil that formed from the lake sediments is extraordinarily fertile, which is why Manitoba and the surrounding areas are among the most productive agricultural regions in the world today. The flat black fields of the Red River Valley are the legacy of 10,000 years of glacial history. Every wheat crop planted there is planted in the memory of the Laurentide. The water that left the Great Plains in the final drainage of the Agassiz system entered the ocean and is now part of the global ocean circulation. Some of it is in the North Atlantic, still affecting the thermohaline circulation that shapes the climate of Europe. Some of it has been cycled through the atmosphere and fallen as rain and snow across multiple continents. Some of it is in the ice cores of Greenland and Antarctica, preserved as layers of oxygen isotopes that record the conditions at the time the snow fell. The water is not gone, it has moved. It is part of the same hydrological cycle that moves water between ocean and atmosphere and land in the same fundamental patterns that have operated for billions of years. The Laurentide ice sheet captured a portion of that cycle for 20,000 years and then released it. And the releasing changed the world. Understanding what happened during that release, in its full geological and human complexity, is one of the projects that researchers across multiple disciplines are still engaged in. The story is not finished. New techniques, new sites, new theoretical frameworks, and new collaborations between Western scientific researchers and indigenous knowledge holders are producing new understanding every year. The ice sheet that once sat over Canada, 3 kilometers thick, pressing the bedrock down toward the mantle and holding the climate of a hemisphere in a cold grip, is a chapter in the story of this continent that has barely begun to be read. The land is still telling it. The traditions are still singing it. And somewhere, in the raised beaches of Hudson Bay, in the flat sediments of the former lake bed, in the stories that have been told for more generations than righted to the stid, the record is there, waiting for the right questions. The single-season phrasing that sometimes appears in discussions of Laurentide deglaciation is not, strictly speaking, what happened. The collapse was fast by geological standards. It involved events that may have occurred within years to decades rather than millennia, but it was not literally a single season. The phrase captures something true about the scale of the contrast between the 20,000 years the ice took to build and the relatively brief period, in geological terms, over which the most catastrophic changes occurred. The 8.2 kiloyear drainage may have happened within a span of years. The abrupt climate transitions visible in ice cores happened within decades. These are not the timescales of geological gradualism. They are timescales that human communities could experience. That distinction matters, because the people who were here when it happened were experiencing it in real time, not in the smooth curves of a climate model, not in the summary statistics of a sediment core, in the rising water and the falling temperatures and the changing landscape and the animals that moved away and did not come back. They experienced it the way all of us experience the world, one day at a time, with incomplete information, doing their best to understand what was happening and to find ways to survive and adapt and keep going. And they did keep going. The communities that existed when the Laurentide began its final collapse are the ancestors, cultural and in many cases biological, of the nations that European colonists encountered when they arrived in the Americas, beginning in the late 15th century. The knowledge traditions, the social structures, the ecological management practices, the astronomical observations, the trade networks, and the oral histories that those nations maintained are the direct inheritors of 10,000 years of post-glacial human experience in North America. They represent one of the longest continuous traditions of landscape knowledge and ecological management on Earth. Understanding the geological story of the Laurentide collapse is not separable from understanding the human story of what North America was before European contact, because the human story begins in the ice. The lake is gone, the ice is gone, the mammoths and the giant ground sloths and the American horses are gone, but the land remembers. The rebound continues, centimetre by centimetre, the bedrock rising back toward where it was before the weight came down. The rivers still follow courses that meltwater first carved. The wetlands still occupy the hollows that ice left. The stories are still told. And the questions, the really good questions, the ones that sit at the intersection of geology and archaeology and oral tradition and climate science and the history of human adaptation, those questions are still being asked. Researchers are still in the field, still in the archives, still in conversation with indigenous knowledge holders who carry in their traditions something that no amount of sediment coring can fully replace, the memory of what it felt like to live through it. The Laurentide ice sheet was one of the most significant features of the Earth's surface for 20,000 years. 3 kilometers thick over Canada, heavy enough to press the continent down toward the mantle, vast enough to reshape the drainage of rivers and the configuration of coastlines across half a hemisphere, and then it went, faster than most people realize, leaving behind a landscape that humans have been reading and managing and living within for 10,000 years. That is the story worth telling, and it is still being told. There is a detail in the geological record that researchers sometimes mention almost in passing, because in the context of the larger story of Laurentide deglaciation, it seems like a minor technical point, but which, when you sit with it for a moment, reveals something profound about the nature of what happened and how we understand it. When glaciologists look at the moraines left by the southern margin of the Laurentide ice sheet, the ridges of rock and debris that mark where the ice sat for long enough to pile up material at its front edge. They find something that does not quite fit the smooth retreat curve. There are places where the moraine sequence, which should show a gradual, stepwise retreat as the ice melted back northward, is missing stages, places where the ice appears to have retreated too fast to leave a clear record. The moraine's jump, or the expected sequence, is absent, and researchers are left inferring rapid retreat from the absence of evidence rather than from its presence. This is one of the signatures of what some glaciologists have called calving retreats or surge events, periods when the margin of the ice sheet moved so quickly that it did not remain in one position long enough to build the moraine ridges that are the usual markers of retreat phases. Calving occurs when ice reaches water, breaks off as icebergs, and floats away. An ice sheet margin that is in contact with water retreats faster than one sitting on dry land because the water itself is doing work that would otherwise require surface melting. The buoyancy of water partially counteracts the ice's weight, reducing the friction that holds the ice to the bedrock and allowing the margin to break off and float rather than requiring that it melt in place. An ice stream, one of the fast-moving zones within an ice sheet that reaches water and begins calving, can deliver ice to the ocean much faster than surface melt could remove it. And as the ice calves and the margin retreats, the remaining ice behind it is pulled forward to fill the gap, which stretches and thins the ice, which makes it more vulnerable to further calving, which accelerates the retreat in the self-reinforcing dynamic that the phrase marine ice sheet instability describes. The question of whether and where this dynamic operated during Laurentide deglaciation is one of the more active research questions in quaternary glaciology. The Hudson Strait, the waterway connecting Hudson Bay to the Labrador Sea and the North Atlantic, was a pathway through which icebergs from the southern and eastern Laurentide were delivered to the North Atlantic during the glacial period. The Heinrich events, which are layers of ice-rafted debris found in North Atlantic sediment cores, represent episodes of massive iceberg production from the Laurentide that occurred periodically during the last glacial period, roughly every 7,000 to 10,000 years. These events, in which layers of rock debris carried from the Canadian Shield by icebergs were deposited on the North Atlantic seafloor as the icebergs melted, are visible in sediment cores as striking layers of coarse material alternating with the finer deep-sea sediment that accumulates between events. The Heinrich events appear to have been produced by surges of ice through Hudson Strait, events in which the ice stream that drained the Hudson Bay sector of the Laurentide surged dramatically, delivering enormous volumes of ice and meltwater to the North Atlantic, and disrupting the thermohaline circulation in ways that produced rapid climate changes across the North Atlantic region. The mechanism behind the Heinrich events is itself a subject of ongoing research. One hypothesis, the binge purge cycle, proposes that the ice stream periodically builds up behind a frozen to bedrock base that stabilizes it, then warms the basal ice through geothermal heat until it reaches the melting point and begins to slide, producing the surge. Another hypothesis involves changes in sea level or ocean temperature, triggering the surge from the marine margin inward. Different researchers favor different mechanisms, and it is likely that more than one process was operating at different times and in different sectors of the ice sheet. What the Heinrich events demonstrate beyond doubt is that the Laurentide was capable of delivering ice to the ocean at rates that significantly disrupted global climate, and that these delivery events were not gradual, but episodic and rapid. The question of whether the final deglaciation of the Laurentide involved a similar but more sustained and ultimately complete version of the same dynamic is a question that the geological evidence raises but does not fully answer. The relationship between the Laurentide ice sheet and the global climate system during its collapse was bidirectional. The ice was responding to climate warming, but the ice was also affecting the climate as it melted. Meltwater entering the ocean changed ocean salinity and density, affecting circulation. Albedo, the reflectivity of the Earth's surface, decreased as white ice was replaced by darker land and water, absorbing more solar energy and accelerating warming. The retreat of the ice exposed land that began to grow vegetation, which changed the carbon cycle as plants captured atmospheric carbon dioxide and as soil organic matter began to accumulate. The retreat of the ice also changed the atmospheric circulation patterns, because the ice sheet had acted as a physical barrier that deflected the jet stream and shaped the distribution of precipitation across the continent. As the ice retreated, the jet stream shifted, precipitation patterns changed, and the regional climates of North America reorganized around a new configuration that progressively approached but did not immediately reach the modern pattern. All of these changes were happening simultaneously, interacting with each other in complex ways that even modern climate models struggle to reproduce accurately when attempting to simulate the deglaciation. The Laurentide collapse was not a simple response to a single external forcing. It was a cascade of interacting processes, each affecting the others, producing a trajectory of change that was overall in the direction of deglaciation, but was punctuated by reversals and accelerations that were not simply proportional to the external climate forcing. The Younger Dryas is the most dramatic example of such a reversal, but there were others, smaller interruptions in the general warming trend that are visible in some proxy records and may reflect temporary reorganizations of ocean circulation or other feedbacks within the system. The people who were living through these oscillations did not know what we now know about the mechanisms driving them. They knew what they experienced. They knew when the summers got shorter and colder. They knew when the fish runs changed. They knew when the caribou shifted their migration routes. They knew when the lake level rose or fell. They did not know that a reorganization of ocean circulation 12,000 kilometers away was the proximate cause of the cooling that was affecting their hunting success. But they responded to what they experienced, adapting their behavior, their subsistence strategies, their seasonal movements, and their social arrangements to match the conditions as they found them. This capacity for adaptive response, for reading changing conditions and adjusting behavior accordingly, is what allowed human communities to persist through the oscillations and catastrophes of the deglaciation period. It is also what makes the oral traditions that encode the memory of those oscillations potentially such valuable sources of information about the specific nature of the changes that people experienced at the ground level. The question of whether specific events in the oral traditions of North American indigenous peoples can be matched to specific events in the geological record is methodologically complex, and researchers working in this area are careful to distinguish between what can be demonstrated and what can only be inferred. The methodology developed by Nunn and Reed and applied by others involves identifying specific geographical claims in the oral tradition, claims that can in principle be verified or falsified by independent geological data, and then testing whether the geological record supports the claim. This is different from the approach of finding a geological event and then looking for oral traditions that might match it, which is prone to confirmation bias. The forward approach, starting from the tradition and testing it against the geology, is more demanding and produces more defensible results. The results so far, across multiple continents and multiple types of geological events, have been sufficiently positive to justify continued work in this direction. The systematic mismatch between the implied timescales of oral tradition preservation and what Western scientific culture has generally assumed about the reliability of oral transmission is forcing a genuine revision of those assumptions. If communities in Australia can accurately preserve geographical information about coastlines that were inundated 7,000 years ago, and the evidence that they can is now strong enough to be published in peer-reviewed geology journals, then the dismissal of North American indigenous oral traditions as unreliable guides to geological history needs to be revisited with the same methodological care. The implications for understanding the Laurentide collapse and its human context are significant. If oral traditions can preserve information about the flooding of coastlines, about catastrophic changes in water levels, about the disappearance of landscapes and the appearance of new ones over periods of thousands of years, then the traditions of the peoples who lived through the Laurentide collapse may contain information about that collapse that we have not yet extracted from them because we have not been asking the right questions or listening with the right frame of reference. This is not a claim that oral traditions contain complete and accurate geological records. It is a claim that some traditions contain some accurate information about some geological events, and that we have good methodological tools now for identifying which traditions those might be and for testing the specific claims they make. Using those tools systematically on the oral traditions of North American indigenous peoples, in genuine partnership with the communities whose traditions these are, is a research agenda that has barely been started. The land claims and treaty rights of indigenous peoples in Canada and the United States are legally and politically separate from the scientific questions about what those peoples' traditions might tell us about geological history, but they are not culturally separate. The argument that indigenous peoples have a deep historical relationship with specific landscapes, a relationship that extends back far beyond the period documented in written records, is supported by both the archaeological evidence of long-term occupation and by the geological evidence that those landscapes have been continuously inhabited since the ice retreated. This does not settle legal questions, which are governed by different standards of evidence and different frameworks of argument, but it does provide important context for understanding what it means when a nation's traditions speak of being connected to a landscape for as long as the world has been as it currently is. For peoples whose oral traditions encode the memory of a time before the landscape was as it currently is, that connection is not metaphorical, it is literal. It extends back to when the ice was here and the land was different, and the traditions say so. The relationship between the geological story of the Laurentide collapse and the contemporary situation of indigenous peoples in North America is not one that most accounts of either subject make explicit. The geological accounts focus on the ice and the climate, with people appearing as occasional contextual elements, but rarely as central actors. The histories of indigenous peoples focus on the political and social dimensions of the colonial period, with the deep geological and ecological context of pre-contact life rarely foregrounded. But bringing these two perspectives into the same frame produces a different picture of both subjects. The people who were here before European contact were not simply inhabitants of a static wilderness. They were the latest generation in a tradition of adaptive management that had been operating in response to a dynamic and changing landscape for 10,000 years. That tradition had survived the oscillations of the Holocene climate, the drainage of Lake Agassiz, the 2-kiloyear cold event, the gradual transformation of the boreal landscape, and 100 other environmental changes that the geological record documents and that the oral traditions may in some cases encode. Understanding that tradition, in its full depth and sophistication, is part of understanding what was lost and what survives in the encounter with European colonization. The tradition of fire management, for example, which has been extensively documented by researchers like Stephen Pine in his monumental work on fire in North America, was not simply a practical tool for improving hunting conditions or clearing land. It was a form of ecological knowledge that had been accumulated over thousands of years of observing how fire affected different plant communities in different seasons and under different moisture and wind conditions, and how the resulting vegetation patterns affected the behavior and distribution of animals. The people doing the burning were not following a simple rule. They were making complex decisions based on detailed ecological knowledge, calibrated to specific landscapes and refined across generations. This knowledge was encoded in cultural practices and oral traditions in ways that allowed it to be transmitted and modified as conditions changed. When that knowledge was disrupted by the forces of colonization, by the suppression of burning, by the removal of peoples from their landscapes, by the destruction of the social structures that maintained and transmitted the knowledge, the result was not simply the loss of a traditional practice. It was the loss of 10,000 years of accumulated ecological intelligence about how to manage the specific landscapes that the Laurentide collapse had produced. The recovery of that intelligence, in whatever forms remain accessible, is one of the more urgent projects of the present moment, because the landscapes that the Laurentide produced are now being subjected to a new set of rapid changes driven by human-caused climate change. The boreal forest is experiencing temperature increases that are significantly above the global average. Permafrost that has been frozen since the last glacial period is thawing. The tree line is shifting northward. The fire regimes are changing. The hydrology of the northern wetlands is being affected by changes in precipitation patterns and evapotranspiration rates. The Arctic sea ice that has been a defining feature of the high north since the last major climate reorganization is declining at rates that exceed what most climate models predicted. In this context, the knowledge of how the post-Laurentide landscape has responded to previous episodes of change, encoded in the geological record and in the oral traditions and in the ecological knowledge systems of indigenous communities, is not merely academically interesting. It is potentially practically useful as a baseline for understanding what a dramatically different climate means for these specific landscapes, and as a guide for thinking about how to maintain or restore ecological function as conditions change. The ice that once sat 3 kilometers thick over Canada shaped everything that came after it. It shaped the bedrock by grinding and abrading it. It shaped the hydrology by carving the lake basins and river valleys and depositing the sediments that are now the soils. It shaped the ecology by creating the blank landscape into which post-glacial plant communities and animal communities moved and assembled themselves over thousands of years. It shaped the human communities by providing the challenge that those communities adapted to, the adversity that selected for the knowledge and social structures and technological capabilities that allowed people to survive and thrive in a dynamic, changing landscape. And in its collapse, in the rapid events and dramatic reorganizations and cascading consequences that the geological record documents, it produced the world that we are standing in now. The story of the Laurentide ice sheet is not finished. It is continuing in the ongoing isostatic rebound that is lifting Hudson Bay centimeter by centimeter. It is continuing in the organic soils of the former lake beds that are now the breadbasket of Canada. It is continuing in the river systems that follow the paths established by glacial meltwater. It is continuing in the traditions of the peoples who have been living in the landscape the ice left behind since before those traditions can be dated. And it is continuing in the research of the scientists and archaeologists and oral tradition scholars who are still in the process of understanding what happened and when and how, and what it meant for the people who were there. The 3 kilometers of ice is gone. Its legacy is everywhere. There is a site in the interior of British Columbia, along the banks of the Thompson River, that gives researchers pause whenever it comes up in discussions of early post-glacial occupation. The site at Milliken, in the Fraser Canyon, has produced evidence of human occupation extending back approximately 9,000 years, placing people in the canyon within a few thousand years of when the Cordilleran ice sheet retreated from that area. But the more significant aspect of the Milliken site, in the context of this story, is what it tells us about continuity. The same canyon, the same river, the same fishing ground, occupied by human communities continuously for 9,000 years. Not continuously in the sense of exactly the same people living in exactly the same spot without interruption, but continuously in the sense of a community relationship with a specific landscape persisting across 90 centuries. The technologies changed, the cultural expressions changed, the specific subsistence strategies shifted as the fish populations and the forest cover and the climate evolved. But people fished the Fraser River at that canyon for 9,000 years. They are still fishing it today. That kind of continuity, that deep attachment to a specific landscape maintained across such extraordinary lengths of time, is one of the most remarkable features of the archaeological and ethnographic record of indigenous peoples in North America. It is also one of the features most consistently undervalued in conventional historical accounts, which tend to treat pre-contact North American societies as either timeless and unchanging, frozen in a kind of eternal prehistoric present, or as fundamentally unstable, constantly being replaced by new waves of migration and cultural change. Neither picture captures what the evidence actually shows, which is communities in dynamic interaction with their landscapes, adapting to change but maintaining a continuity of attachment to place that extends back to the earliest period of post-glacial occupation. The Fraser Canyon at Milliken was not an arbitrary choice of settlement location. The canyon is a natural funnel for migrating salmon on their way upstream to spawn, and the Thompson River confluence at that location creates hydrological conditions that make fishing particularly productive. The people who first occupied the site, 9,000 years ago, recognized these conditions and established a presence there that their descendants maintained for 90 centuries. The ecological knowledge encoded in that presence, the understanding of when the fish run peaks, where the best fishing platforms are, how to preserve and store salmon for the winter, what other resources are available in the surrounding landscape in different seasons. That knowledge accumulated over 9,000 years of continuous occupation is of a depth and specificity that could not be replicated by any amount of external observation or scientific study of the river. It is knowledge that can only be produced by living with a landscape across generations. The same principle applies across the continent. The peoples of the Ohio River Valley who built the Hopewell earthworks had been living in that valley for thousands of years before the Hopewell tradition reached its florescence. Their knowledge of the landscape, the river dynamics, the soils, the plant communities, the animal behavior, was not recently acquired. It was the accumulation of thousands of years of observation, encoded in cultural practices and oral traditions, and it shaped the decisions that went into where to build the earthworks, how to orient them relative to the landscape, how to use them in the seasonal round of subsistence and ceremony. The earthworks are not evidence of primitive astronomy or primitive engineering. They are evidence of a sophisticated tradition of landscape knowledge that included astronomical observation as one component of a larger system of understanding the relationship between the human community and its environment. This brings us to a question that underlies much of the discussion about the pre-Columbian history of North America, a question that the story of the Laurentide collapse makes unavoidably concrete. What was lost when European colonization disrupted the communities and knowledge traditions that had developed over 10,000 years of post-glacial history in North America? Not in an abstract or political sense, but in a specific, concrete sense. What specific knowledge about what specific landscapes and ecological systems and astronomical cycles and social management techniques was encoded in the traditions and practices that were disrupted or destroyed during the colonial period, and what would it take to recover it? The loss was immense, and it was not uniform. Some traditions were more successfully maintained than others. Some communities were more completely disrupted than others. Some knowledge systems were more amenable to being encoded in material forms that survived, or were more successfully transmitted in conditions of disruption than others. The result is a patchwork, a landscape of surviving and lost knowledge that varies by community, by region, by the specific nature of the colonial disruption experienced, and by the degree to which communities have been able to maintain or revive their traditions in the centuries since first contact. What is clearer than it has ever been, based on the convergence of research in archaeology and genetics and ecology and oral tradition studies, is that the pre-Columbian societies of North America were not primitive forerunners of civilization, not simple hunter-gatherers living lightly on a wilderness landscape. They were the sophisticated inheritors and continuators of 10,000 years of ecological management and landscape knowledge, developed in direct response to the challenges and opportunities created by the collapse of the Laurentide ice sheet and the transformation of the continent that followed. The ice shaped the land shaped the people shaped the land in return, and that process of mutual shaping, playing out over 10,000 years, produced the North America that European colonists found when they arrived, a continent that looked wild to them, because they did not have the eyes to see the 10,000 years of human management that had produced what they were looking at. The raised beaches of Hudson Bay, where the land is still rising from the rebound, preserve in their stratigraphy layers of occupation, of campfires and shell middens and tool scatters that mark the passage of communities across the landscape as the shoreline rose and the geography changed. Researchers walking those raised beaches today are walking through time, the most recent beaches closest to the present shore, the older beaches further inland and higher up the slope, each successive bench representing the shoreline at a specific period of the rebound. The human occupation record embedded in those benches spans the entire history of human presence in the region, and the fact that people were using those beaches, camping on them, fishing from them, leaving their traces in the sediments, at every stage of the rebound that is detectable archaeologically, tells you something important. The landscape was never empty. It was always being used, always being known, always being incorporated into the cultural and ecological knowledge of the communities that lived within it. The ice is the beginning of this story, but not its end. The story continues in the rebound and the rivers and the raised beaches and the traditions and the research. It continues in the communities that maintain their connection to these landscapes today, carrying forward knowledge accumulated across 10,000 years of post-glacial life. It continues in the scientific understanding that is still being built, the geological and archaeological and climatological research that is still in progress, still producing new findings that shift the picture in ways that matter for how we understand both the past and the present. And it continues in the larger conversation about what it means to know a landscape to have that knowledge embedded in traditions and practices and social structures, and what happens when that knowledge is threatened or disrupted, and what it takes to sustain or recover it. The 3 kilometers of ice that once sat over Canada changed everything about the land it sat on. It is gone now, melted into the ocean, the water distributed around the globe, the record of its melting preserved in sediment cores and ice cores and coral records and the raised beaches of Hudson Bay. What it left behind is a continent still bearing its marks, still responding to its absence, still being understood in the full depth of what its presence meant and what its going produced. The geological story and the human story are not separate. They are the same story, told from different vantage points, across different timescales, but converging on the same landscape, the same events, the same question of what it means to live in a world that was shaped by ice and is still becoming what the ice made it. The people who were here watched the ice go. Their descendants have been living in the landscape it left behind for 10,000 years. That is the story behind the story of the 3 kilometers of ice. And it is still going on. The Ojibwe word for Lake Superior is Gichigami, meaning great sea or great water. It is one of the oldest place names in continuous use in North America, and it encodes in its meaning something true about the landscape it names. Lake Superior is not simply a large lake. It is a remnant of the glacial landscape, a basin carved by ice and filled with meltwater and rain over thousands of years, connected to the other Great Lakes in a hydrological system that drains the remnant of what was once the southern margin of the Laurentide ice sheet. When Ojibwe communities named Gichigami, they were naming a feature of the post-glacial landscape that their ancestors had known since the ice first retreated from the Lake Superior basin. The name has been in continuous use for longer than most languages currently spoken in the world have existed. It is, in its own way, a piece of the geological record, a human mark on a landscape that the ice made. The Ottawa River, which drains much of the southern Quebec highland and forms the border between Ontario and Quebec before flowing into the St. Lawrence, follows a course that was established by meltwater drainage from the retreating Laurentide. Its valley is a former meltwater channel, carved by the enormous volumes of water flowing south and east as the ice retreated northward. The Algonquin peoples, who have lived in the Ottawa Valley for thousands of years, have traditions that speak of the river and the landscape of the valley in terms that reflect a deep, long-term knowledge of its character and history. The river has been central to their subsistence, their travel, their trade networks, and their cultural life for as long as their traditions extend. The same river that was carved by glacial meltwater, the same valley that was filled by a post-glacial lake before the land rebounded enough to drain it. The landscape carries the history, the traditions carry the knowledge, and the research is still in the business of connecting them. There is no clean ending to a story like this one. The geological processes are ongoing, the research is ongoing, the traditions are living, the landscapes are still being understood, still being managed, still bearing the marks of 10,000 years of post-glacial history and the deeper history of the ice that preceded them. What the story of the Laurentide ice sheet collapse offers, if you are willing to sit with its full complexity rather than reducing it to a simple narrative, is a different way of thinking about time and about the relationship between the past and the present, not as history that is safely over and done with, but as process that is still underway, still producing consequences, still being interpreted and understood by the communities that live within it and by the researchers who study it. The land is still rising in Hudson Bay, 12 millimeters a year, the rebound from an ice sheet that disappeared 8,000 years ago. The Earth is slow to respond, but it responds. And when it does, everything on its surface moves with it. The story of what the Laurentide ice sheet did to the drainage of the Mississippi River Basin is one of the more dramatic chapters in the post-glacial history of North America, and it has direct implications for understanding the human communities of the continental interior. The Mississippi River system today is the largest river drainage system in North America by area, covering roughly 3.1 million square kilometers. During the last glacial maximum, the southern margin of the Laurentide sat somewhere across what is now the upper Midwest, and the meltwater from that margin drained southward through precursor channels of what would eventually become the modern Mississippi-Missouri system. The volumes involved were extraordinary. During peak meltwater pulses, the discharge of the Mississippi River was many times its modern flow. The river carried enormous quantities of sediment, building the broad alluvial plain that now makes up the lower Mississippi Valley, depositing sand and silt across a swath of landscape from Memphis to the Gulf of Mexico that is still the most productive agricultural land in North America in terms of soil depth and fertility. The Lewis Hills of Iowa, Nebraska, and Missouri, those distinctive bluffs of wind-blown silt that give the landscape along the eastern edge of the Great Plains a character unlike anywhere else on the continent, are another direct product of Laurentide deglaciation. The silt that forms lows was ground from rock by the ice and deposited in the outwash plains in front of the glacier. From there, prevailing westerly winds picked it up and carried it eastward and southward, depositing thick beds of fine material that today form the substrate of some of the most productive farmland in the world. The farmers of the Midwest are farming soil made by the Laurentide ice sheet. The wheat of Saskatchewan and the corn of Iowa both grow in glacially derived soils. The connection between the ice that was here 20,000 years ago and the food on contemporary tables is more direct than most people realize. The pre-contact peoples of the Mississippi Valley lived in and along one of the most dynamic river systems in the world, a system that was still actively reorganizing itself in response to the changes initiated by glacial deglaciation. The Mississippi regularly changed course, particularly in its lower reaches, through a process called avulsion, in which the river abandons its existing channel in favor of a shorter, steeper path to the sea. These channel switches could be relatively rapid by human standards, playing out over centuries, and they could dramatically change the character of specific locations along the river. A community that had established itself along a productive oxbow lake, a curved remnant of a former river channel now cut off from the main flow, would find that lake gradually filling in and losing its character over generations. A community at the confluence of a tributary with the main channel would find that confluence shifting as the river adjusted its course. The landscape of the lower Mississippi Valley was not static. It was a dynamic, shifting system, and the communities that lived within it had to understand its dynamics to survive. Cahokia, the pre-Columbian city that occupied the American bottom, the broad alluvial floodplain at the confluence of the Missouri, Illinois, and Mississippi rivers just east of modern Street. Louis was built at one of the most hydrologically complex locations on the continent. The American bottom is a product of glacial and post-glacial sedimentation, a thick accumulation of alluvial material deposited by the convergence of river systems draining the retreating Laurentide. The soils of the American bottom are extraordinarily fertile, a fact that was not lost on the people who chose to build one of the largest pre-Columbian cities in North America on those soils. Cahokia at its peak, roughly between 1000 and 1200 CE, supported a population estimated at between 10 and 20,000 people, with a surrounding region population of perhaps 40,000 or more. It was the largest city north of Mexico. It was built on land that the ice sheet had made. The question of why Cahokia rose when it did, and why it subsequently declined, is one of the more actively debated questions in North American archaeology. The rise of Cahokia appears to coincide with a period of favorable climate in the American bottom, a series of warm, wet years that may have increased agricultural productivity and made the support of a large urban population more feasible. The decline of Cahokia after approximately 1200 CE coincides with evidence of climate stress, including flooding events and drought periods, that may have made the intensive agriculture on which the city depended more precarious. The relationship between climate variability and the trajectory of Cahokia is not a simple story of climate determinism, because the political and social factors involved in the rise and fall of complex societies are not reducible to climate alone. But the climate context is important, and it connects Cahokia to the longer story of post-glacial climate variability that began with the collapse of the Laurentide and has continued, with different mechanisms, through the Holocene. The people of Cahokia and the broader Mississippian tradition that Cahokia represented were farming communities in a way that distinguishes them from the earlier archaic and woodland peoples who had managed the landscape primarily through hunting, gathering, and burning. The adoption of maize agriculture, which spread northward from its origin in Mesoamerica over a period of centuries and reached the eastern woodlands of North America sometime around 1000 CE, transformed the possibilities for population density and social complexity in ways that the earlier food economies had not allowed. Maize, combined with beans and squash in the Three Sisters intercropping system that had been developed by indigenous agricultural communities in Mesoamerica, provided a highly productive and nutritionally complete food base that could support large, densely settled populations in ways that the hunting, gathering, and burning economy could not. The adoption of maize was not a straightforward improvement in every respect, as the skeletal evidence from Cahokia and related sites shows an increase in nutritional stress markers and in dental caries associated with a high-starch diet, but it was a transformation in the scale and organization of human societies in North America that built on the ecological and social foundations developed over the preceding 10,000 years of post-glacial history. The transformation of the landscape associated with Mississippian agriculture was itself a continuation of the longer tradition of indigenous landscape management, now intensified and organized around permanent field systems and the requirements of a grain-based food economy. The clearing of forest for fields, the maintenance of those fields against regrowth, the management of water in the floodplains through levees and drainage channels, and the selection and breeding of maize varieties adapted to the specific conditions of different parts of the continent. All of these represent the application of accumulated ecological knowledge to new purposes and new scales. The Mississippian agricultural landscape was not a wilderness. It was a managed, productive, humanized landscape built on the ecological foundations of the post-glacial landscape that the Laurentide had shaped. The same principle applies in the Great Plains, where the agriculture of the Missouri River horticulturists, the Mandan, Hidatsa, Arikara, and related peoples, was based on the cultivation of maize, beans, squash, and sunflowers in the rich bottomland soils along the Missouri and its tributaries. The Missouri River, like the Mississippi, is a post-glacial river whose course and character was established by the routing of meltwater from the retreating Laurentide through a landscape reshaped by ice. The bottomland soils that the horticulturists farmed are glacially derived soils, deep and fertile from the deposition of glacial sediments over thousands of years of river flooding. The communities that farmed those soils had been in the region long enough to understand its hydrological character intimately. Their agricultural practices, including the selection of field locations and the timing of planting relative to the flood cycle of the river, reflected knowledge accumulated over generations of observation and practice. The Mandan and Hidatsa were, by the time European contact occurred in the 18th century, among the most sophisticated agricultural communities on the Great Plains, maintaining large earth lodge villages in permanent locations along the river and producing agricultural surpluses that supported a far-ranging trade network connecting the horticulturist villages with the nomadic hunting peoples of the surrounding plains. The Lewis and Clark expedition, which wintered with the Mandan in 1804 and 1805, recorded extensive observations of the Mandan agricultural system, social organization, and trade networks. The picture that emerges from those records, and from the subsequent ethnographic and archaeological work at Mandan and Hidatsa sites, is of communities with a deep, sophisticated relationship with their specific landscape, a relationship built on knowledge accumulated over the centuries of occupation and refined through the specific demands of maintaining a permanent agricultural community in a dynamic, variable river environment. The relationship between the glacial past and the pre-contact agricultural present in the Great Plains interior is not simply one of landscape inheritance. It is also a story of climate variability and adaptation. The Great Plains have experienced significant drought periods throughout the Holocene, including a period known as the mid-Holocene altithermal or Holocene climatic optimum, between roughly 8,000 and 5,000 years ago, when temperatures in the interior of the continent were several degrees warmer than today, and precipitation was significantly reduced. During this period, the archaeological record of the southern and central plains shows a reduction in population density and evidence of communities moving toward better watered areas along rivers and springs. The recovery of the plains environment after the altithermal, as precipitation increased and temperatures moderated, was followed by a re-intensity of human occupation and the development of the specialized bison hunting economies that characterized the plains in the centuries before European contact. The patterns of expansion and contraction of human occupation in the plains through the Holocene are a testimony to the continuing importance of climate variability in shaping the human geography of the post-glacial landscape. These climate oscillations were not, for the communities that experienced them, abstract statistical phenomena. They were droughts that killed crops and dried up water sources. They were flood years that inundated fields and carried away stored food. They were good hunting seasons and bad ones. They were winters of unusual severity or springs of unusual warmth. They were the conditions that forced communities to make decisions about whether to stay in a location or move, whether to change a subsistence strategy or maintain it, whether to draw on trade networks for food or provide food to others through those networks. The communities that survived across the long span of post-glacial time in North America were the communities that had developed the knowledge, the social structures, and the adaptive flexibility to navigate this variability without being destroyed by it. That is a significant achievement. It is an achievement that the conventional narrative of pre-contact North America, with its emphasis on timeless traditional cultures living in equilibrium with their environments, systematically undervalues. The climate changes of the present moment, driven by anthropogenic greenhouse gas emissions, are producing changes in the North American landscape that in some ways parallel and in some ways exceed the changes of the post-glacial period. The Arctic and subarctic are warming at rates 2 to 4 times the global average, with consequences for permafrost, sea ice, hydrology, and the ecological communities that depend on the cold conditions that have characterized those environments throughout the Holocene. The boreal forest is experiencing fire regimes that are outside the range of historical variability, with more frequent and more extensive fires that are transforming the character of the forest. The glaciers of the western mountains, including what remains of the Cordilleran ice in the ranges of British Columbia and Alberta, are retreating rapidly. The rivers fed by those glaciers are likely to experience reduced summer flows as the glacial contribution to their hydrograph decreases. The landscapes that the Laurentide made are themselves being remade by a new set of forces. In this context, the knowledge traditions of the communities that have lived in and managed these landscapes since the ice retreated are not merely historical curiosities. They are potentially crucial sources of information about how these landscapes have responded to climate variability in the past and about management approaches that have been tested over thousands of years in those specific environments. The recovery and application of that knowledge, in genuine partnership with the communities whose traditions these are, is one of the more important and underappreciated dimensions of the contemporary conversation about climate adaptation in North America. The story of the Laurentide ice sheet collapse is ultimately a story about adaptation, about communities that faced conditions of rapid and dramatic change and found ways to survive and persist. It is a story about the knowledge that was accumulated through that process and encoded in traditions that, in many cases, are still alive today. It is a story about a landscape that was shaped by an event of geological proportions and that has been managed, modified, and known by human communities ever since. And it is a story that is not finished, because the landscape is still changing, the traditions are still being maintained and adapted, and the research is still producing new understanding that shifts the picture. The ice was here, it changed everything, it left. And what it left behind became the world that the people of North America have lived in for 10,000 years, the world whose transformation we are now in the middle of again. When researchers drill ice cores from Greenland, they are reading the Laurentide's history. The oxygen isotope ratios preserved in each annual layer of the ice core record the temperature of the year in which the snow that became that layer fell. The layers go back more than 100,000 years in the longest cores, preserving a detailed record of climate variability across multiple glacial cycles. The Younger Dryas transition, the abrupt warming 11,700 years ago, appears in the Greenland ice cores as a change that occurred within a decade or two in some records. This is not geological timescale change. This is change that happened within a single lifetime, in the lifetimes of people who were living in North America at the time. The ice cores show us that the world the Laurentide made, and then unmade, was not a world of gradual, predictable change. It was a world of abrupt transitions, rapid reorganizations, and discontinuities that would have been profoundly disorienting to any community that experienced them. The communities that survived those transitions are the communities whose descendants we are still in contact with today. The Anishinaabe of the Great Lakes, the Cree of the Boreal Forest, the Inuit of the Arctic coast, the nations of the Pacific Northwest, the peoples of the Great Plains and the Mississippi Valley, all of them trace their presence in these landscapes back through the post-glacial period, back through the transitions and disruptions recorded in the ice cores, back to the time when the Laurentide was retreating and the land was becoming what it now is. They are not people without history. They are people with more history in these specific landscapes than any other human beings alive. The ice cores also record something else, something that connects the ancient story of the Laurentide collapse to the contemporary moment in a way that should not be overlooked. They record the beginning of the industrial era, marked by the appearance in the ice of trace elements and compounds associated with fossil fuel combustion and industrial processes. The record in the ice of what human beings have been doing to the atmosphere since the mid-19th century is clear and unambiguous, and the record shows that the rate of change currently underway in the climate system is not comparable to the gradual warming that characterized most of the Holocene. It is comparable in rate, if not in mechanism, to the most rapid transitions in the deglaciation record, the transitions that the people of 10,000 years ago had to adapt to in real time. The difference is that those people did not know the mechanism. They knew the symptoms, the warming, the flooding, the changing seasons, the shifting animal distributions, the disappearing landscapes, but they did not know why it was happening. We do know why the current changes are happening. That knowledge gives us something that the people of the deglaciation did not have, the possibility of addressing the cause rather than simply adapting to the consequences. Whether we use that possibility wisely is a question that the geological record of the Laurentide collapse, with its stories of rapid transition, community adaptation, knowledge loss, and the long, slow work of rebuilding ecological relationship with transformed landscapes, can inform but not answer. The ice is telling us something. The raised beaches of Hudson Bay, still rising at 12 millimeters per year, are telling us something about what happens to landscapes when massive amounts of weight are removed. The traditions of the peoples who have lived in the post-glacial landscape for 10,000 years are telling us something about what it takes to maintain knowledge and community across periods of radical change. The sediment cores and ice cores and coral records are telling us something about how the climate system responds to perturbations and what the consequences of those responses have been for the human communities living within them. What we do with what we are being told is, as always, a human choice. The ice cannot make it for us. The geological record cannot make it for us. The traditions and the knowledge of the communities that have persisted across 10,000 years of post-glacial change can inform it, but only if we are willing to listen, and to listen seriously, not as tourists collecting wisdom from exotic sources, but as participants in a shared landscape who need what other participants know. The Laurentide ice sheet was 3 kilometers thick over Canada. Its collapse changed the world. The story of that change, in its full geological and human complexity, is still being told. We are, all of us who live in North America, living in its aftermath. And the question of how to live well in the aftermath of catastrophic change, the question that the people of the post-glacial transition faced and answered in their various ways, over the 10,000 years that followed, is a question that remains. In the present moment, urgently alive. The ice came, the ice went, the land remains. The people remain, the knowledge remains, where we have the wisdom to look for it, and the patience to listen to what it says. The specific question of what happens underground when a massive ice sheet sits on top of the land for 20,000 years, and what happens after it goes, is one that researchers have been investigating with growing sophistication over the past several decades. And the answers they are finding are relevant not only to geological understanding, but to a surprising range of contemporary practical concerns. The weight of the Laurentide ice sheet suppressed the land beneath it, as we have discussed, but it did more than simply press the land down. It affected the flow of groundwater through the bedrock beneath it. It changed the geochemical conditions in the uppermost layers of the Earth's crust. It created conditions under the ice that in some places produced what geologists call subglacial lakes, bodies of liquid water trapped between the base of the ice and the bedrock below, kept liquid by the combination of geothermal heat from the Earth's interior and the insulating weight of the ice above. These subglacial lakes, which have been most extensively studied beneath the modern Antarctic ice sheet, where the largest of them, Lake Vostok, has been a subject of intense research for decades, were also features of the Laurentide system, and their drainage history is potentially part of the story of meltwater pulses and rapid climate changes during the deglaciation. The concept of subglacial lakes matters for the story of what the ice left behind. When the ice retreated and the pressure was released, the groundwater systems that had been compressed and altered by the weight of ice above them began to reorganize. Water that had been trapped in pore spaces of rock under pressure began to move. Springs appeared in locations where there had been none before, as pathways for groundwater flow were opened by the retreat of the ice and the rebound of the land. Some of these springs, fed by groundwater that had been resident in the rock under the ice for thousands of years, carried chemical signatures reflecting their history under extraordinary conditions. And those signatures have been useful to researchers trying to understand the conditions that prevailed under the ice during the glacial period. The karst systems of the Canadian Shield and the surrounding sedimentary rock provinces were affected by glacial overriding in complex ways. Karst, the landscape formed by the dissolution of soluble rock, such as limestone, dolomite, and gypsum, by slightly acidic groundwater, is one of the most geologically dynamic of all landscape types. The glacial period affected karst development in some areas by filling cave systems with glacial sediments, and in other areas by the direct erosion of the overlying rock by the moving ice. The post-glacial period opened new pathways for karst development in some areas as the pressure was released and groundwater systems reorganized. The result is a complex patchwork of karst features across the landscape of eastern and central Canada, some of which preserve evidence of conditions that existed before, during, and after the Laurentide occupation. The caves and sinkholes of the Bruce Peninsula of Ontario, the Niagara Escarpment, and the limestone terrains of southern Ontario and Quebec preserve within their sediments to records of the ice advance and retreat that are distinct from, but complementary to the records preserved in lake sediments and in the ice cores. Cave sediments, which accumulate very slowly and in conditions of relative stability compared to surface environments, can preserve organic materials that allow direct radiocarbon dating of the timing of cave occupancy and cave sediment deposition. The speleothems, the stalactites and stalagmites, and other calcium carbonate formations that grow in caves, grow only when liquid water is moving through the cave, and they stop growing when conditions freeze or dry. The record of speleothem growth and interruption in caves of the post-glacial Canadian landscape encodes a detailed record of the timing of the return of liquid water after the ice retreated, which is another way of dating the retreat itself. Indigenous communities in the Great Lakes region have traditions involving caves and underground features of the landscape that researchers have been examining with new interest in the context of the broader turn toward taking oral traditions seriously as potential archives of geological information. The Ojibwe traditions of the underwater panther, Mishipeshu, the great horned creature associated with the deep places of the Great Lakes and their underground connections, are not simply mythological constructions. They reflect a deep familiarity with the character of the lakes and the dangerous underwater features of their geography, including underwater caves, currents, and unpredictable depths, that was accumulated over thousands of years of living on and around these bodies of water. Whether specific elements of these traditions encode information about the formation of the lakes during and after the glacial period is a question that has been discussed but not systematically investigated, partly because the methodological tools for such investigation have only recently been developed, and partly because the research partnerships necessary for doing it respectfully and productively are still being built. The Great Lakes themselves are among the most studied glacial features in North America, and for good reason. They are the largest system of freshwater lakes in the world, containing roughly 21% of the world's surface fresh water. Their formation is inseparably tied to the history of the Laurentide ice sheet. The basins in which they now sit were carved by glacial ice, moving southward and southwestward from the central dome of the Laurentide, grinding into the relatively soft sedimentary rocks of the Great Lakes Basin, while leaving the harder Precambrian rocks of the Canadian Shield to the north relatively more intact. The differential erosion of hard and soft rock by the ice produced the basin and ridge topography that the Great Lakes now occupy, with the lakes sitting in the softer rock basins and the resistant rock forming the peninsulas and islands of the lake margins. The filling of the Great Lakes basins with water was not a simple process. As the ice retreated northward, the meltwater in front of the ice margin initially drained south and southwest through river systems, eventually reaching the Gulf of Mexico. As the retreat continued and the ice margin moved north of the lake basins, the lakes began to fill to levels that were controlled by the available outlets, which changed as isostatic rebound lifted the land in the north and as the retreating ice margin exposed new lower outlets. The history of Great Lakes levels through the post-glacial period is a complex story of rise and fall, controlled by the interplay of meltwater input from the retreating Laurentide, the changing elevation of outlets as isostatic rebound proceeded, and eventually the contribution of precipitation over the lake basins as the glacial input diminished. At various times during the post-glacial period, the Great Lakes were connected to each other in configurations very different from the modern one, and their levels were either significantly higher or lower than today. Lake Nipissing, a phase of Great Lakes history centered roughly at 4,000 to 5,000 years ago, saw lake levels in Lake Huron and Lake Michigan significantly higher than their current levels, leaving wave-cut terraces and beach ridges that are still visible above the modern lake margins. At other times, lower outlets allowed the lakes to drain to levels below those of today. The beaches and terraces of these different lake levels are among the most studied features of the post-glacial landscape of the Great Lakes region, and they have been correlated with the archaeological record of occupation to show that human communities were present on the lake shores throughout the various phases of lake level change, adjusting their location and activities to the changing shoreline. The fisheries of the Great Lakes, which were central to the subsistence economy of indigenous communities around the lakes throughout the post-glacial period, reflect the history of the lakes themselves. The fish species of the Great Lakes represent a mixture of species that colonized the lakes as they formed and stabilized, spreading from refugia in the south and east where fish populations had persisted through the glacial period, and species that entered from different directions as lake connections changed. The extraordinary diversity of the Great Lakes fish fauna, including the lake trout that have been a keystone species in the subsistence economy of Great Lakes communities for thousands of years, reflects the geological history of the lakes and the ecological history of their colonization and development. Understanding that history is part of understanding the human history of the Great Lakes region, because the fish ecology of the lakes shaped the subsistence strategies, the settlement patterns, and the cultural traditions of the communities that lived on their shores. The copper trade that moved Lake Superior copper across the Great Lakes region and beyond, as part of the Old Copper Complex and later the Hopewell Exchange networks, was possible partly because of the geological history of the Lake Superior Basin. Lake Superior sits over a sequence of Precambrian rocks that includes the Keweenaw Peninsula copper deposits, where native copper occurs in unusually high concentrations in the pore spaces of ancient basaltic lava flows. These lava flows were themselves the product of geological events more than 1 billion years before the Laurentide, when a massive rift in the Earth's crust was trying to split the continent apart before the process stalled. The copper deposits formed in association with that ancient rifting event. The Laurentide ice sheet scoured the overlying rocks, exposing the copper at the surface, and in some places, concentrating native copper boulders and nuggets on the glacial outwash plains and lake beaches where people could find them without any need for deep mining. The glacial erosion and the subsequent filling of the Lake Superior Basin with water made the Lake Superior copper deposits accessible to the people who found and exploited them, and the extraordinary trade network that developed around that copper was made possible by a geological sequence extending from ancient rifting through glacial erosion to post-glacial lake formation. This is the deep geological context that most narratives of pre-Columbian North American trade and culture omit, not because it is irrelevant, but because the conventional disciplines are not organized to tell this kind of multi-scale story. The history of ancient copper trade is typically told as a cultural or economic story. The geology of Lake Superior is typically told as a geological story. The connection between them, the fact that the specific copper deposits of Lake Superior are a product of billion-year-old rifting that was made accessible by glacial erosion and post-glacial lake formation, and that the resulting trade network shaped the social and cultural development of communities across a vast area of the continent for thousands of years. that connection tends to fall between the disciplines, but it is a real connection, and it is illustrative of the broader point about the relationship between the geological history of the post-glacial North American landscape and the human history of that landscape. The land that the Laurentide shaped is not just a stage on which human history happened, it is a participant in that history, providing the specific resources, the specific constraints, the specific opportunities that shaped what communities could do and how they organized themselves and what knowledge they needed to develop. The copper of Lake Superior, the salmon of the Fraser Canyon, the bison of the post-glacial grasslands, the fertile soils of the former Agassiz lakebed, the fish of the Great Lakes, the caribou of the retreating tundra margin. All of these resources, and the communities that depended on them, are connected to the history of the Laurentide ice sheet and its collapse. The story of post-glacial North America is a story of the deep integration of geological and human history, the story of a landscape made by ice and the communities that have been in conversation with that landscape for 10,000 years. It is a story that is still being written in the ongoing rebound of Hudson Bay, in the continuing research of scientists and oral tradition scholars and archaeologists working in partnership with indigenous communities, in the management decisions being made by those communities today about how to respond to a new set of rapid environmental changes. And it is a story that matters, not only for understanding the past, but for thinking clearly about the present and the future. The 3 kilometers of ice left its mark on everything. On the rocks, on the rivers, on the soils, on the climate, on the oceans, on the human communities that have been living in its aftermath for 10,000 years. And now, in a time of new rapid change, understanding what the ice did and how the communities that followed it adapted and persisted across the long span of post-glacial time, that understanding is one of the most important things we have to offer ourselves as we face what is coming. The land remembers, the traditions remember, the ice cores remember. We are the ones doing the remembering. The Mackenzie River, which drains the largest river basin in Canada, covering approximately 1.8 million square kilometers of the Northwest Territories, Alberta, British Columbia, and parts of Saskatchewan and Nunavut, is another product of the post-glacial reorganization of drainage in North America. During the last glacial maximum, the area now drained by the Mackenzie was partially covered by the Laurentide ice sheet and partially by smaller mountain glaciers from the Cordilleran system. As the ice retreated, the Mackenzie drainage system developed and organized itself around the new topography created by glacial erosion, capturing drainage from areas that had formerly flowed in different directions. The river today carries an enormous discharge of fresh water and sediment to the Beaufort Sea, contributing to the distinctive freshwater plume that extends into the Arctic Ocean from the Mackenzie Delta and influences the oceanography of the Western Arctic. The Mackenzie watershed contains some of the most extensive permafrost in the world, and that permafrost is itself a product of the post-glacial climate of the region. Permafrost, ground that remains frozen throughout the year, develops when mean annual air temperatures are cold enough to maintain soil temperatures below zero over periods of decades to centuries. The permafrost of the Mackenzie Basin has been building and developing since the ice retreated and the climate of the region settled into its Holocene pattern. In some areas, permafrost extends to depths of hundreds of meters. In others, particularly in the southern and transitional zones, it is more patchy and less continuous. The distribution and character of permafrost across the Mackenzie Basin reflects the detailed local variation in climate, vegetation, and soil conditions that has developed over the past 8 to 10,000 years. The Dene peoples, whose traditional territories cover much of the Mackenzie Basin, have a detailed knowledge of the permafrost landscape that they have inhabited for thousands of years. They know where the ground is stable and where it is prone to subsidence, where water drains through the soil and where it is blocked by permafrost and forms wetlands, where the permafrost is shallow enough to be affected by changes in vegetation cover and where it is deep enough to be stable over human timescales. This knowledge, which is essential for making decisions about where to camp, where to travel, where to find reliable water sources, and where to find the animals and plants that constitute the subsistence base, is encoded in place names, in oral traditions, in the accumulated experience of generations of observation and practice. It is landscape knowledge of the same deep type that we have been discussing throughout this story, knowledge that connects the communities that possess it to the geological history of the land they live in, knowledge that the Laurentide ice sheet and its retreat made possible and necessary. The permafrost of the Mackenzie Basin is now thawing, in ways and at rates that are outside the range of variability that the Dene and other permafrost zone peoples have experienced in their historical tradition. The warming temperatures of the anthropogenic climate change era are penetrating to depths and achieving rates of ground temperature increase that, in some areas, are causing rapid thaw of permafrost that has been frozen for hundreds or thousands of years. The consequences for landscape stability are significant. Thermokarst, the irregular terrain produced by the thawing and collapsing of permafrost, is developing in areas that were formerly stable. Riverbeds are eroding as permafrost beneath the banks thaws and the banks slump into the water. Buildings and infrastructure built on the assumption of stable permafrost are being affected as the ground beneath them changes character. And the ecological communities that depend on permafrost conditions, including specific plant communities, nesting birds, and the drainage patterns that create the wetlands on which migratory waterfowl depend, are being affected. The Dene and other indigenous peoples of the permafrost zone are experiencing and documenting these changes in ways that are providing researchers with ground-level observations that complement the satellite and remote sensing data, the specific local knowledge that allows a Dene elder to recognize that the behavior of a particular lake or riverbank has changed in ways that have no precedent in their memory, or that a permafrost feature that was stable for as long as anyone can remember is now moving, is observational data that the instruments cannot fully capture because the instruments lack the baseline of generations of continuous observation that indigenous observers possess. This is another dimension of the argument that indigenous knowledge systems are scientifically valuable, not merely culturally significant, and that research and management decisions affecting these landscapes should be informed by those knowledge systems rather than treating them as peripheral or merely supplementary. The thawing permafrost of the Mackenzie Basin is also a climate feedback that researchers take seriously in their projections of future warming. Permafrost contains enormous quantities of organic carbon, the accumulated remains of plants and animals that have been frozen in place for thousands to tens of thousands of years without decomposing. As the permafrost thaws, this organic material is exposed to microbial decomposition, releasing the carbon stored in it as carbon dioxide and methane, both greenhouse gases that contribute to further warming. The potential scale of this feedback is large enough to affect global climate projections significantly if the thawing proceeds at the rates that some scenarios project. The organic carbon stored in the permafrost of the Arctic and subarctic, including the Mackenzie Basin, represents the accumulated product of thousands of years of biological productivity in the post-glacial landscape, frozen and preserved by the same cold conditions that the Laurentide ice sheet established and that have persisted in modified form since the ice retreated. The ice is gone, but its legacy includes the permafrost, and the permafrost stability is now in question. This is a story that connects the geological past to the ecological present and the climate future, in ways that the conventional narrative of either subject tends to obscure. The carbon stored in the permafrost of the Mackenzie Basin was being accumulated by plants that were growing in the post-glacial landscape over the past 8,000 years. Plants growing in conditions established by the retreat of the Laurentide and the subsequent development of the boreal and tundra ecosystems of northern Canada. The Dene and other peoples of the region have been managing that landscape through burning and hunting and other practices throughout that period. The ecological conditions that produce the carbon storage are partly a product of that management, and the potential release of that carbon in the current period of rapid warming is a consequence of a new set of perturbations to which the existing management practices are not adapted, precisely because those practices were developed and refined under conditions very different from the ones now being produced by anthropogenic climate change. The circle closes, or rather spirals, connecting the geological history of the ice, the human history of adaptation, to the post-glacial landscape, the ecological knowledge systems that those adaptations produced, the contemporary challenge of rapid change exceeding the pace of historical variability, and the question of what knowledge and what approaches might help navigate that challenge. The Laurentide ice sheet collapse is not simply a geological episode of the distant past. It is the origin story of the contemporary landscape of North America, and understanding it in its full complexity is part of understanding what we are dealing with now and what we might learn from the communities that have been navigating the aftermath of that collapse for 10,000 years. The geological record of the Laurentide provides one kind of knowledge about the landscape: the chronology of events, the rates of change, the magnitudes of perturbation, the mechanisms of ice sheet behavior, the global consequences of meltwater discharge. The oral traditions and ecological knowledge systems of the indigenous peoples of North America provide a different kind of knowledge: the ground-level experience of living in a dynamic landscape over thousands of years, the accumulated wisdom about how specific environments behave and what they require of the communities that depend on them, the long perspective that comes from having your community's survival depend on understanding landscape dynamics across timescales that exceed individual and even generational memory. Both kinds of knowledge are necessary for a complete understanding of the post-glacial North American landscape. Neither is sufficient on its own. The scientific community's engagement with indigenous knowledge systems has been expanding and deepening in the recent decades, driven partly by the recognition that indigenous knowledge can provide information and perspectives that instrumental records and geological proxies cannot, and partly by the ethical and political imperatives of working respectfully with the communities whose landscapes and traditions are involved. This engagement has not always been easy or uncontested, because the histories of extraction and appropriation of indigenous knowledge without attribution or benefit sharing are long, and the damage they did is real. Building research partnerships that are genuinely collaborative, that recognize indigenous knowledge systems as authoritative within their domains, rather than merely as supplementary data sources, and that ensure that the communities whose knowledge is involved have control over how it is used and benefit from the research, requires ongoing work and genuine commitment. But the partnerships that have been built in this way and the research they have produced have been among the most productive in terms of new understanding of the post-glacial North American landscape. The Laurentide ice sheet is gone. Its absence is the foundation of everything we see when we look at the landscape of Canada and the northern United States today. The flat prairies, the Great Lakes, the boreal forest, the rivers and wetlands of the Shield Country, the raised beaches of Hudson Bay, the Loess Hills of the Midwest, the alluvial soils of the river valleys. All of these are the legacy of a mass of ice that once covered 12% of the Earth's land surface, and then, in geological terms, very quickly melted away. The rapidity of that melting, the events and feedbacks within it, and the consequences for global climate and for the human communities of North America are still being fully understood. The research is ongoing. The story is still being told. And the communities that have been living in the aftermath of that collapse, managing and knowing and adapting to the landscape it produced for 10,000 years, are still here. Their presence is itself a form of testimony to what the ice made possible and what human adaptability and persistence can accomplish across the long span of post-glacial time. They are the living connection between the geological story and the human story, the people who have been reading the landscape that the ice left behind long enough to know it in ways that instruments and models and sediment cores cannot fully capture. The 3 kilometers of ice pressed down on the Canadian Shield. The Shield is still rising. The story of that pressing and that rising, and everything that happened in between and after, is the story of North America. It is the story of a continent shaped by cold and by the transformation that followed the cold, and inhabited by people who have been here since before the transformation was complete, people who watched the world change and found ways to live in what it became. That is the story, and it is still going on. There is a question that researchers and educators sometimes ask when presenting the geological story of the Laurentide to audiences unfamiliar with glaciology, a question that crystallizes something important about scale and perception. If you were standing in southern Ontario 12,000 years ago, would you be able to see the glacier? The answer depends on where exactly you were standing and in which direction you were looking, and on the specific year within the deglaciation sequence you happened to be in. At the maximum of the Younger Dryas, the ice margin may have been close enough to southern Ontario to be visible from high ground on a clear day, a white horizon, a glare in the sky, the sense of cold coming off the ice mass to the north. But at most times during the post-Younger Dryas retreat, the ice margin would have been further north, too far to see directly from most of southern Ontario. What you would have seen were the effects: the meltwater rivers, the kettle lakes, the raw glacial till that had been ground from the bedrock and deposited across the landscape, the sparse, tundra-like vegetation of the periglacial zone, the edge of the world as you knew it. People were there to see those effects, to experience those edges. The earliest sites in southern Ontario and adjacent areas date to the period just following the final retreat of the ice from those areas, showing that people moved into newly available terrain quickly. The question of how quickly is partly a question of how attractive the newly deglaciated landscape was compared to the environments further south that people were already occupying, and partly a question of how long it took ecological conditions in the newly available terrain to reach a threshold of productivity sufficient to support a human population. The evidence from southern Ontario and the Great Lakes region suggests that both hunter-gatherers and the fish populations they pursued expanded northward relatively rapidly after the ice retreated, establishing the foundations of the Great Lakes' archaic traditions that would persist and develop for thousands of years. The landscape of southern Ontario today, with its rolling topography shaped by glacial deposition, its Great Lakes coastlines, its moraines and drumlins and eskers marking the passage of the ice, preserves the visible record of the Laurentide's presence and retreat. Every drumlin, that elongated hill shaped like an inverted spoon, was formed under moving ice, aligned with the direction of ice movement. Every esker, that long, sinuous ridge of coarse sediment, marks the path of a subglacial meltwater stream that deposited its sediment load as it flowed under the ice. Every kettle lake, occupying a depression left by a block of stagnant ice that melted in place after being buried by outwash sediment, is a memorial to the final stages of the ice's presence. The landscape is a text, and researchers who know how to read it can reconstruct in considerable detail the sequence of events that produce the terrain. The people who live in this landscape today, whether they know it or not, are living in a space shaped by the most recent glacial period, walking on ground that was still under ice 12,000 years ago, drinking water from aquifers recharged by glacial meltwater, farming soils made from glacially ground rock. The connection between the geological past and the present is not abstract or remote. It is immediate and material. It is in the clay beneath the foundations of houses, in the gravel of riverbeds, in the depth of the topsoil. The Laurentide made this landscape, and the landscape makes the life that happens within it. Understanding that connection, sitting with the knowledge that the ground you are standing on was under 3 kilometers of ice, not so very long ago, in geological terms, and that everything you can see in every direction is the product of that ice's presence and departure, does something to the sense of scale. It puts the human span of recorded history, 5,000 years, into a context where it is less than half the time since the ice left. It makes the 10,000 years of indigenous occupation before European contact feel less like prehistory and more like a span of time comparable to all of written civilization, a span during which real and sophisticated things were happening. Knowledge was accumulating, landscapes were being managed, communities were rising and falling and adapting and persisting, and it makes the current moment of rapid environmental change feel less like an unprecedented rupture and more like a new and particularly acute episode in a long history of climate variability and community adaptation, one that calls for the same qualities that previous episodes demanded: knowledge, flexibility, cooperation, and the deep patience that comes from taking the long view. The ice was here, it left. What it left has been the home of human communities for 10,000 years. And now those communities, the indigenous communities that have been here since the beginning of the post-glacial period, and the communities that arrived more recently and are still learning what this landscape is and what it requires, are facing a new set of rapid changes that will test the same qualities that the post-glacial transitions tested. The story of the Laurentide collapse is not merely the story of a geological event in the distant past. It is a story about what happens when the world changes faster than communities can easily adapt, and about what it takes to navigate that change and come out the other side with knowledge intact and community intact and connection to the land intact. It is, in that sense, a story for now. There is a particular kind of silence that comes when you stand at the edge of Hudson Bay on a calm August day and look north. The water stretches to the horizon, grey-green in the summer light, enormous and still. The tidal flats at the margin are wide and flat, exposed by the low tide that reveals the shallow shelf of the bay's southern coast. Shorebirds move across the mud, picking at the invertebrates that live in the tidal zone. In the distance, beluga whales move through the bay, white shapes briefly visible at the surface before they dive. The scale of the place is difficult to apprehend. The bay covers more than 1 million square kilometers, stretching 700 kilometers from north to south and more than 1,000 kilometers from east to west at its widest. It is one of the largest bodies of water in the world, and it was, until 8,000 years ago, filled with ice. The communities that live around Hudson Bay today, the Cree and the Inuit and the Oji-Cree, whose traditional territories include the bay's shores and the rivers that drain into it, have been connected to this landscape since before the bay was a bay. Their ancestors were present in the regions south and east of the ice as the Laurentide retreated northward, and they moved into the newly exposed terrain as soon as conditions allowed. The knowledge traditions of these communities encode an understanding of the bay and its surrounding landscape that is measured in thousands of years of continuous relationship, not in decades or centuries. They know the bay the way you can only know something you have lived with across that kind of time. The Hudson Bay lowlands, the vast flat plain of peat bogs and fens and shallow lakes that surrounds the southern margin of Hudson Bay, is one of the world's largest wetland complexes. It covers roughly 350,000 square kilometers and stores enormous quantities of carbon in the accumulated peat that has been building since the ice retreated. The peat accumulation began shortly after deglaciation, as the first plants colonized the newly exposed terrain and began the long process of building organic soils. Thousands of years of plant growth and incomplete decomposition, preserved by the cool, wet conditions of the boreal environment, have built peat deposits that in some areas are many meters deep. The carbon stored in those deposits represents the accumulated photosynthesis of tens of thousands of years of plant life, carbon that was captured from the atmosphere and stored in the soil rather than being returned to the atmosphere through decomposition. This carbon storage function of the Hudson Bay lowlands is now being affected by the same warming that is thawing permafrost further north in the Mackenzie Basin. The peat bogs of the lowlands are warming. In some areas, they are drying out as evapotranspiration rates increase in response to higher temperatures, changing the character of the wetland from carbon-storing sphagnum bog to drier, more decomposition, active environments. In other areas, particularly where permafrost underlies the peat, thawing is causing the land to subside and lake formation to expand, changing the hydrology of the wetland complex in ways that affect the balance between carbon storage and carbon release. The net effect of these changes on the carbon balance of the Hudson Bay lowlands is a question that researchers are studying intensively because the potential for the region to shift from a carbon sink to a carbon source, as decomposition of stored peat exceeds the rate of new peat formation, has significant implications for global carbon budgets and for climate projections. The Cree communities of the Hudson Bay lowlands have been observing these changes, and the changes they describe in their lands over the past several decades are consistent with, and in some cases, more specific than what the instrumental records show. They describe changes in the behavior of rivers and lakes. They describe changes in the character of the bog surfaces, areas that were formerly stable and dry that are now wet and unstable, areas that were formerly flooded that are now drier. They describe changes in the distribution and timing of animal movements that are related to changes in vegetation and water conditions. They describe changes that they did not see in their lifetimes before roughly the last 2 to 3 decades, and that their elders, when consulted, confirm are outside the range of the variability they remember, and that the traditions they inherited describe. The land they are observing changing is land their ancestors knew when it was under ice. The magnitude of the transformation is not lost on them. The research that links the geological history of the Hudson Bay region to the contemporary changes being observed there is not simply academic. It has direct relevance to decisions being made right now about resource extraction, about infrastructure development, about climate adaptation strategies, and about the future management of landscapes that indigenous communities have been managing for thousands of years and that are now changing in ways that require new thinking about what management means and what it can accomplish. The historical perspective that the geological and archaeological record provides, combined with the long-term observational knowledge that indigenous communities possess, is a combination that is more powerful than either source of knowledge on its own. The story of the Laurentide ice sheet collapse, in its full scope from the geological mechanisms of ice sheet dynamics, through the human experience of the communities that lived through the deglaciation and built their lives in the landscape it produced, to the contemporary implications of that history for understanding present and future changes in the North American landscape, is a story that spans multiple scales of time and multiple ways of knowing. It is a story that requires the integration of geological and climatological science, of archaeology and anthropology, of oral tradition and ecological knowledge, of indigenous perspectives and Western scientific frameworks. No single discipline and no single community can tell it completely. What this kind of story does, when it is told in its full complexity, is change the frame. It makes the conventional boundaries between geological history and human history, between deep time and recorded history, between scientific knowledge and indigenous knowledge, less rigid and more permeable. It suggests that the story of North America does not begin with European contact or with the development of agriculture or even with the end of the Pleistocene. It begins much earlier, in the ice, and it runs continuously from the ice to the present day, through the communities that have inhabited this landscape and the knowledge they have accumulated and transmitted and adapted across 10,000 years of post-glacial time. The single season of the title, the season in which the ice sheet seemed to vanish, is a compression of a longer process into a frame that captures something true about the scale of contrast between the time the ice took to build and the time its most catastrophic changes took to play out. The ice built over 100,000 years. The most dramatic events of its collapse played out in years to centuries. That is not literally a single season, but in geological terms, in the scale of the ice sheet's history, it is close enough to a single season to be a meaningful comparison. And in human terms, in the lifetimes of the communities that experienced the most rapid events, the draining of Lake Agassiz, the 2-kilo-year cold event, the Younger Dryas termination, those events were experienced as the kind of rapid, world-transforming change that fits within a human lifetime or a few generations. They were experienced, in the communities that went through them, as something like a single terrible season of transformation, after which the world was different and everything had to be rethought. The rethinking that those communities did, across the generations following the most acute phases of the deglaciation, produced the knowledge systems and social structures and ecological management practices that sustained North American indigenous communities for 10,000 years before European contact. Understanding that achievement, taking its full measure, is part of understanding who the people of the Americas were and are, and what was lost and what survives in the encounter with European colonization, and what the knowledge traditions that do survive might offer to a world facing a new set of rapid and profound changes. The ice is the beginning, the stories are still continuing, and the land, the patient, rising, rebounding, remembered land of the post-Laurentide landscape, is still telling the story of what happened when the ice went away. Listen to it long enough, with enough different ears, scientific and indigenous and geological and human, and you start to hear what it is saying. The ice was here, the ice changed everything. The ice went, and the people, remarkable and adaptable and knowledge-rich and connected to the land in ways that the conventional history of North America almost never acknowledges, have been here ever since, reading the landscape that the ice made, managing it and knowing it and telling its story in their own way, in their own language, in their own time. That is the story worth telling. That is the story that the 3 kilometers of ice, and its going, and everything that followed, is asking us to tell. And now you have heard it, lying in the dark somewhere on the vast continent that the ice shaped, listening to a voice telling you what the land remembers. The ice is gone, the land is still rising, and the story is still going on. The specific geological feature, known as the Laurentide ice sheet, left behind a set of scientific puzzles that continue to generate productive disagreement among researchers, and those puzzles are worth examining in some detail, because they illuminate not just the history of the ice, but the state of the science that is trying to understand it. One of the more persistent debates concerns the question of how much of the global sea level rise associated with deglaciation can be attributed to the Laurentide specifically, as opposed to other ice sheets, particularly the Antarctic and the Greenland ice sheets, that were also losing mass during the same period. The answer matters because understanding which ice sheets were melting fastest during the deglaciation and in what sequence is crucial for understanding both the mechanisms of rapid ice loss and for calibrating the models that scientists use to project the future behavior of the ice sheets that still exist. The problem is that the sea level record, as preserved in coral reefs and other geological proxies, records the combined effect of all ice sheets melting simultaneously, plus the gravitational and rotational effects that cause sea level to change differently in different parts of the world as different ice masses shrink. Separating the contributions of different ice sheets from the global sea level signal requires sophisticated modeling of the gravitational effects, combined with careful analysis of where sea level rose most and where it rose least during specific events. The pattern of sea level change around the world during an ice sheet melt event is different for each ice sheet, because the gravitational field of a large ice mass actually pulls ocean water toward it. And as the ice melts and that gravitational attraction decreases, the nearby ocean actually drops while the far-field ocean rises. This counterintuitive effect means that researchers looking at the sea level record at different locations around the world during the same event can be reading different signals from the same global process. The mathematical techniques for unraveling these effects, which involve modeling both the gravitational and the Earth's rotational response to changing ice masses, have been developed primarily over the past 3 decades as computing power has made the calculations feasible. They have been applied to the problem of Laurentide melt contributions with increasing sophistication, and the results have generally supported the conclusion that the Laurentide was the dominant contributor to the sea level rise between approximately 18 and 8,000 years ago, with contributions from other ice sheets being secondary, though not negligible. But the uncertainties remain significant, particularly for the specific rapid events like meltwater pulse 1a, where the signal is large enough to require a major ice sheet contribution but the specific source is still debated. The question of how fast the Laurentide could have lost mass is constrained from multiple directions. Glaciological theory provides upper bounds on how fast ice can flow and carve. The geological record of moraine positions and glacial landforms provides constraints on the pace of margin retreat in specific sectors. The sea level record provides constraints on the total meltwater production over specific time intervals. And ice core records from Greenland, which were accumulating snow throughout the period of Laurentide deglaciation and recording the climate conditions of those times, provide a detailed atmospheric record against which the ice sheet behavior can be calibrated. Putting all of these constraints together produces a picture that is considerably more detailed than what was possible 2 or 3 decades ago, but still has important uncertainties, particularly in the areas where the geological record is sparse or poorly preserved. The Hudson Strait sector of the Laurentide is one area where researchers believe they may have a case study of something like the rapid collapse dynamics that are most relevant to contemporary concerns about modern ice sheets. The Hudson Strait, the narrow but deep waterway connecting Hudson Bay to the Labrador Sea, appears to have been the pathway through which an ice stream drained a substantial portion of the southern and central Laurentide during the Heinrich events described earlier. The specific Heinrich event that coincides with, or perhaps triggered, the Younger Dryas is known as Heinrich Event 1, and it is recorded in North Atlantic sediment cores as a particularly dramatic layer of ice-rafted debris. The connection between Heinrich Event 1 and the Younger Dryas is not fully resolved, with different researchers attributing different causal weights to the iceberg discharge itself, versus the meltwater accompanying it, versus other mechanisms. But the evidence that a major surge of the Hudson Strait ice stream occurred around the time of the Younger Dryas onset is clear from the sediment record. What this means for the communities that were living in North America at the time of Heinrich event, one is a question that the archaeological record does not answer directly, partly because the population density of North America was lower at that time than it was in later periods, and partly because the preservation of archaeological sites from the period before 13,000 years ago in areas close to the period ice margin is poor. But the climate consequences of Heinrich Event 1, which appear to have been global in scale, would have been felt by every community in North America that depended on seasonally consistent climate conditions for its subsistence. The cooling associated with the Younger Dryas, following on the heels of the warming pulse that had been proceeding since the last glacial maximum, would have reversed the expansion of habitable area that the initial warming had produced, pushing the tundra steppe boundary southward again and contracting the range of conditions suitable for the subsistence strategies that communities in the transition zone had been developing. The communities that survived the Younger Dryas reversal and the subsequent rapid warming at its termination are among the most adaptable in the documented record of human ecological history. The pace of the climate change they experienced at the Younger Dryas termination, with temperatures rising by 10 degrees Celsius in Greenland within decades, is comparable in rate, if not in absolute magnitude, to the warming projections for the current century under high-emission scenarios. The communities that navigated that change did so with stone tools, with fire, with oral tradition, with social networks spanning hundreds of kilometers, and with the ecological knowledge accumulated by previous generations operating under different conditions. They did not survive by applying a fixed strategy that had worked before. They survived by adapting, by drawing on the flexibility inherent in social networks that spanned multiple environments, by finding ways to extract nutrition from rapidly changing landscapes, and by transmitting knowledge of what was changing to the people who would need to act on it. This is not a model that maps cleanly onto the contemporary situation, which involves different mechanisms, different scales, and different options for response. But it is a reminder that the human capacity for adaptation to rapid climate change, while not unlimited, has been demonstrated in practice at rates of change comparable to what contemporary projections describe. The communities that demonstrated that capacity were not doing so from a position of technological sophistication in the conventional sense. They were doing so from a position of deep ecological knowledge, extensive social networks, and the cultural flexibility to change behavior when conditions changed. Those qualities are not irrelevant to contemporary adaptation challenges. They may be, in fact, among the most important qualities to cultivate and preserve. The story of the Laurentide ice sheet and its collapse is, at its deepest level, a story about the relationship between geological time and human time, between the scale of the Earth's climate systems and the scale of human communities and human knowledge. The ice moved on timescales that dwarf recorded history, but its consequences were felt on timescales that individual human beings and human communities could experience, could adapt to, could encode in their traditions and their practices, and pass on to their descendants. The geological and the human are not as separate as the conventional disciplinary boundaries suggest. They intersect in the landscape, in the knowledge systems that have been developed in response to that landscape, and in the ongoing conversation between the changing land and the communities that have been reading and managing it for 10,000 years. The ice sheet is gone, but the story of its going is not over. It continues in the rising land and the changing climate and the living traditions and the ongoing research. It continues in the conversations between scientists and indigenous knowledge holders that are producing new understanding of what the landscape is and what it has been. And it continues in the simple geological fact that the ground is still moving, rising imperceptibly but measurably every year in response to a weight that was removed 8,000 years ago. The Earth is slow to respond, but it responds. And the response is still happening, right now, under the feet of everyone who stands on the land that the Laurentide made. 3 kilometers of ice, gone, in geological terms, almost overnight. The landscape it made is still here, still being understood, still being lived in and managed and studied and told about. The story of what happened when the ice went away is the story of this continent, and it begins where all the deepest stories begin, in the cold, in the darkness under the ice, in the slow accumulation of pressure that eventually, inevitably, seeks release. The ice had to go somewhere. It went into the ocean rose, the land emerged, the people were already there, and 10,000 years of living followed. You are living in that 10,000 years. The ice is your inheritance, and the story of its going is the story of how the world you live in came to be. Rest now, the land is still here, the rebound continues, and somewhere, in the archives of the lake sediments and the ice cores, and the traditions of the people who have known this landscape since before the ice was gone, the full story is still being told, one layer at a time, one generation at a time, one slow centimeter of rising ground at a time. The ice was here. Now, you are here. And the story between those two things is longer and stranger and more remarkable than you probably knew before tonight. The archaeological record of the period immediately following the Younger Dryas termination, the period known as the Early Archaic, that begins roughly 10,000 years ago and runs for several thousand years, shows communities in North America diversifying their subsistence strategies in ways that directly reflect the rapid environmental changes they were navigating. In the eastern woodlands, as the forests of birch and spruce that had characterized the periglacial landscape were replaced by warmer-adapted deciduous forest of oak and hickory and maple, communities shifted their subsistence emphasis to reflect the new resource base. The nuts of the deciduous forest, particularly acorns, provided a storable carbohydrate resource that the earlier tundra-edge communities did not have access to. The white-tailed deer, which expanded northward with the warming forests, became a central subsistence resource for eastern communities in ways that the caribou and the large grazers of the glacial edge steppe had been before. The river systems reorganized as the hydrology of the region changed, and communities that had been mobile, following wide-ranging animal populations across large territories, began in some areas to adopt more territorial, less mobile strategies centered on predictable, abundant, seasonal resources like river fish runs and nut harvests. This shift toward greater sedentism and more intensive use of smaller territories is one of the defining characteristics of the Archaic period across much of North America, and it reflects the post-Younger Dryas landscape changes in ways that researchers have been documenting systematically. Communities were not simply adapting to a fixed new environment. They were adapting to an environment that was itself still in the process of stabilizing after the most dramatic climate transitions, still shifting in its species composition, still reorganizing its hydrology, still developing the soil communities and vegetation structures that would characterize the mature Holocene landscape. This was a moving target, and the communities chasing it were doing so without the benefit of the kind of long-term baseline knowledge that their descendants would develop over the subsequent thousands of years. The knowledge that was developed during the early and middle Archaic, the deep ecological understanding of specific landscapes that was encoded in oral traditions and cultural practices and social structures, is the foundation on which all subsequent pre-Columbian North American cultural development was built. The mound builders and the Hopewell Trade Network and Cahokia and the agricultural communities of the Mississippi Valley were all built on the accumulated ecological intelligence of thousands of years of adaptive management of the post-glacial landscape. That intelligence did not appear suddenly or mysteriously. It was built, generation by generation, by communities reading their landscapes carefully and transmitting what they learned to those who came after. The ice made the landscape shaped the knowledge, and the knowledge made possible everything that came after. This is the through line, the Laurentide ice sheet, 3 kilometers thick over Canada, collapsing in what the geological record describes as rapid events occurring over decades to centuries, rather than the millennia you might expect, is not simply a geological curiosity or a chapter in the history of climate science. It is the origin of the North American landscape as it exists today, and the origin of the 10,000-year tradition of ecological knowledge and community adaptation that sustained the pre-Columbian peoples of North America across the full range of environmental variability that the Holocene produced. Understanding it changes what you see when you look at the landscape. It changes what you hear when you listen to the traditions of the people who have known that landscape the longest. And it changes what you think about when you consider the changes that are now being imposed on that landscape by a new and different kind of forcing. The ice was here. The ice went. The story of what happened in between, and everything that followed, is still being told. And now you have heard a part of it, lying somewhere in the dark on the continent the ice made, listening to the voice of a story that began in the cold. The Peyto Lake, in Banff National Park, one of the most photographed lakes in Canada, sits in a cirque carved by a glacier that is now retreating. The glacier that carved the cirque was part of the Cordilleran ice system, the companion to the Laurentide that covered the mountains and western interior of British Columbia and extended into the ranges of Alberta and Montana. The retreat of Peyto Glacier is documented in photographs stretching back more than a century, showing the progressive diminishment of the ice that has been ongoing since the end of the Little Ice Age and accelerating in recent decades. The lake that the glacier feeds, and whose extraordinary turquoise color is produced by the suspended glacial flour that the ice grinds from the rock, will change character as the glacier retreats. The glacial flower input will decrease. The color will shift. The lake that exists today is a function of the glacier that exists today, and both are in the process of change. The people who have known Peyto Lake and its valley for thousands of years, the Stony Nakoda, among others, have watched the glacier and the lake across a time frame that the photographic record cannot begin to capture. Their traditions encode observations of the landscape that extend back to the period when the Cordilleran ice was present in far greater extent than it is today, and their knowledge of the specific character of the landscape, the behavior of the river fed by the glacier, the seasonal patterns of the lake and its surrounding terrain, represents an observational baseline that no instrumental record can match in depth. The loss of that observational baseline, as the communities that possess it are separated from the landscapes they know by the pressures of contemporary life, and as the landscapes themselves change faster than the traditional knowledge systems were designed to track, is a loss of a different kind than the loss of the glacier itself. Both are happening, both matter. The Bow River, which flows from the glaciers and snowfields of the Canadian Rockies through Calgary and across the southern prairies to join the South Saskatchewan River, has been a central feature of the landscape for the Blackfoot and Stoney and other peoples of the region for thousands of years. Its character, its seasonal flow regime, its fish populations, its relationship to the surrounding land, are encoded in the traditions and practices of those communities in ways that represent thousands of years of careful observation. The river is fed partly by glacial meltwater, partly by snowmelt, and partly by precipitation. As the glaciers of the headwater region retreat, the glacial meltwater contribution to summer flows will decrease, affecting the timing and magnitude of the river's seasonal pattern. This is not a distant projection. It is already happening, and the communities that depend on the river and that have the deepest knowledge of its normal behavior are among the best positioned to observe and document the changes. The story of the Laurentide ice sheet collapse is, in its most expansive reading, the story of how ice shapes the world and how the world shapes the communities that live within it. The ice that covered Canada was not a passive feature of the landscape. It was an active geological agent, grinding and sculpting and depositing and holding water that would otherwise have been in the ocean. Its collapse was not simply a passive response to warming. It involved feedbacks and accelerations and catastrophic drainage events that were produced by the dynamics of the ice sheet system itself, interacting with the warming climate in ways that produced outcomes more rapid and more dramatic than simple proportional response. And its legacy, in the landscape of lakes and rivers and wetlands and fertile soils and still-rising bedrock, is the physical foundation of everything that human communities in North America have built over the past 10,000 years. That foundation is not static. It is still changing. The bedrock is still rising. The rivers are still adjusting their courses. The climate is changing again, more rapidly than at any time since the end of the Younger Dryas, and the landscape is responding. The communities that have the deepest knowledge of this landscape, the indigenous communities that have been reading and managing it since the ice retreated, are observing changes that fall outside the range of their historical experience. And the scientific community is documenting changes that fall outside the range of the instrumental record. The convergence of these two observation systems, the long-term indigenous observational tradition and the short-term but globally distributed instrumental record, is one of the more powerful tools available for understanding what is happening and why. The ice that was here shaped everything, its going changed everything, and now, 10,000 years after the landscape settled into what we think of as its natural configuration, it is being changed again. The communities that know this landscape best have been here through the last great change. Their knowledge of what the land can do and has done is the deepest baseline we have. Listening to that knowledge and integrating it with the knowledge produced by the instruments and the models and the sediment cores is the most important conversation we can be having about this landscape right now. The Laurentide ice sheet is gone, but the story of its going and everything that followed is the most important story about North America that most people have never heard. Now you have heard it, and the land, patient and rising and remembered, is still telling it. The 3 kilometers are gone, the 12 millimeters per year continues, and the story between the going and the rising is the story of this continent, still unfolding, still being told, still asking to be heard by anyone patient enough to listen in the dark. The ice gave this continent its shape. The people gave this continent its soul. Both facts belong in the same sentence and in the same story, because neither is complete without the other. This is that story, and it ends, as all the best geological stories do, not with a conclusion, but with the land still moving, still becoming, still carrying the memory of the ice in the very texture of its rising. The story continues. It has always been continuing. It will not stop.